So good morning, Seki-san.
Hi, good afternoon. Good morning. Good morning for you.
Yes, good afternoon to you. How are you?
Fine. And you?
Yeah, good, thanks.
Okay.
So you will chair this session?
Yes, yes. Shall we start?
Maybe.
You should wait a bit.
I don't know, it's 10 now. Maybe a little bit more people will join, only 25. Maybe we could wait 1 or 2 minutes more.
Okay.
Yes, thanks.
All right. So can you hear me?
Yes, yes.
Okay, shall we start? So good morning for Indian people and good afternoon for Japanese participant. So my name is Seki. I'm chairing this session 3. This session will have 5 invited talks. And the first talk will be given by Dr. Spankal Vedanta from Mysore, India. So Spankal, so please share your screen.
Yes. Okay. Do you see my screen now?
Yes, perfect.
Okay, so should we start?
Okay, so he will talk about the exciting physics at the interface of organic semiconductor ferromagnet heterostructures. Okay, please, Spankal.
Yeah, all right. Thank you so much, Professor Takeshi Seki, for this kind introduction. It's a great pleasure to be here and organize this conference, and most importantly, also present some of our recent work. Yesterday, Dr. Brajbhushan Singh presented this work on spin pumping with topological insulators. We're actually working quite a bit on that. But for today's talk, I focused on the organic spintronics. And I will discuss in next 25 minutes or so how you can explore a lot of novel physics in such organic semiconductor ferromagnetic heterostructure. So we'll understand the importance of these images as we move in. So yeah, let me put this pointer. Yes. Before I go to the talk, I like to just bring to your attention that we are organizing this W2S webinar series on spintronics every Thursday in the evening, Indian time, and sometime depending on the speaker's geographical location, we shift a little bit the talk time, but it's mostly every Thursday. So far, 82 talks have been held, and we are continuing. So I welcome, if you want to join, you can write an email to this address, and we will be happy to add you in the list. So this is, you can say, like our group's research activities. One of the major components we work with domains and fermion dynamics. We have different architecture like dot array, anti-dot arrays, and we have a strong cooperation with Professor Koki Takanashi and Professor Takeshi Seki on that, where we have worked a little bit on these dots and anti-dots of iron platinum L10 ordered systems, and got very nice publications. Some of them are listed here. Then another major area is where we are looking at the spin to charge conversion physics. We are inverse spin-Hall effect with topological insulator that you have seen yesterday from Brajbhushan Singh's talk. We are also working with antiferromagnets, then the transition metal dichalcogenides, organic semiconductor and so on. So some of the papers are listed here. Then, but all these things mostly involving high spin orbit coupling materials. At the same time, you can use low spin orbit coupling material for something called organic spintronics, where the interest is a little bit different, and some representative papers are actually put here. So we are working on various type of materials, and you can see that, yeah, so there are a little bit different interests, but they're all interconnected in a way for SOT kind of domain or fermion switching for future data storage, power efficient memories. So before I go to the talk, I like to thank my group who have actually done the work, and I'm very fortunate to have a very nice set of groups. This is kind of old photo, much before the corona. We have not taken actually from our group photo recently. So many of the student postdoc, they are actually somewhere like Sijoni Malik, who started this work on organic spintronics. So she is now a postdoc at Thales, working closely with Professor Manuel Bibes and Professor Albert Fert. And Saugata is another former student who is a postdoc now directly working with Professor Albert Fert at Thales. And some students have left, some master students, and the people where the circles are there, they have actually contributed to the work which I'm going to present today. And I'm also greatly thankful to all my collaborators, which includes, Professor Seki, Professor Takanashi, Professor Kubota, Professor Mizuguchi, who are part of this conference, Professor Anjan Burman, and many others who have been really a great support for us. I'm also acknowledging the funding from different agencies, parent organization is Department of Atomic Energy, but also DST and many other funding agencies. So, as I said, these organic semiconductors are a very interesting class of materials. They possess low spin orbit coupling, they have almost no hyperfine interactions and so on. And mostly, if you see organic semiconductors are diamagnetic. Now the question is, can you somehow make these diamagnetic substances magnetic? So it is possible if you put it next to a ferromagnet, then that can be something called charge transfer physics, and a spin interface phenomena will occur. And that spin interface can actually modify the global anisotropy of the system, the domain structure, the Magnetization universal, and so on, that I will discuss today. Then the next question is, can you use this organic semiconductor for Zylonsky-Moria interaction? So yesterday we have heard few talks, in particular Professor Anil Kumar, where he talked, and also Professor Anjan Burman, where they talked about the Zylonsky-Moria interaction at different interfaces, mostly heavy metals like platinum or tantalum. Professor Anjan Burman also talked about graphene. So the question is here, like the organic semiconductors like C60 or others, can you use it for tuning DMI physics? And the answer is yes, and that I will also show that how you can tune it, and probably in future you can also use it for making chiral domain physics or fermions. Then another thing, we know that the organic semiconductors like C60, which contains only carbon-based elements, so they are all low atomic number elements. So the spin orbit coupling is also very less. Now, can you enhance somehow the spin orbit coupling? And it seems yes. And due to certain characters called curvature enhanced spin pumping, spin orbit coupling, and that can lead to spin pumping and ISHE, and it can actually lead to enhancement of damping and clear inverse spin-Hall effect. So all these things I will discuss. Let's first talk about the spin interface physics and its implications on the domains, anisotropy, and Magnetization universal. So how would you actually explain this, organic spintronics? So let me just show this nice picture on Indian food that's very famously known as biryani. So it's, let's say, chicken biryani. So how the chef prepares this food? He makes a container with the chicken, which is already kind of prepared. Then he puts a layer of rice, then again a layer of chicken, then again a layer of rice. Then he covers the container and he mildly warms up. And after some time, the flavor of the chicken actually goes inside the rice. So if I give you only the rice from this big container, I don't give you any chicken, and you eat, you can still feel that this is chicken biryani because the flavor of chicken has gone inside the rice. So same way, you can explain the interface physics, where you have a ferromagnetic film on top of a substrate, and you have certain thickness of the ferromagnet, it's some material, you measure its magnetic properties like saturation, magnetization, saturation field, coercivity, magnetic moment, and so on, maybe domains and so on. Now you take the same system and just deposit a diamagnetic organic semiconductor like C60. Then in principle, the magnetic property of the system 2 should be same as system 1, because the ferromagnetic entity is exactly the same, identical, only you have deposited a diamagnetic organic semiconductor. But in reality, you will see this is not the case, because at the interface, something will happen and you will have a spinterface which will actually modify the magnetic properties of the system 2 quite strongly. And you can explain in a very simple way using this very nice diagram given by Sanbito and others almost 10 years back, where they have shown that if you have a ferromagnetic element and you have an organic semiconductor, it's quite far apart from each other, then you see the density of states at the Fermi level, there is a band splitting, which tells the ferromagnetic nature of this material. And if you see the density of states of the organic semiconductor, there is no band splitting at the Fermi level. That means it's simply a diamagnet. Now you bring this molecule on top of the ferromagnet, like here or here, then you see immediately for the organic molecule, there is a band splitting. That means the organic molecule, which was diamagnetic, now it is becoming ferromagnetic. That's remarkable because you are making a non-magnetic substance into magnetic by so-called, it's like a proximity effect, and you are making some kind of charge transfer and, hybridization. The physics is very simple actually. Carbon has, empty orbitals, partially filled orbitals, so it can take electrons. And if you put it next to a ferromagnetic metal like iron, cobalt, nickel, or even some other metals, it is possible that the charge transfers can happen and hybridization will occur between the pi d orbitals of the carbon and ferromagnet, and you can have a hybridization and charge transfer, which will lead to some induced magnetism in carbon, and that's what we are going to discuss. So very quickly, some literature. This was one of the nice papers from the group of Professor Oscar Cespedes, where he has taken a cobalt and C60 multi-layer system. Yesterday, we have heard the talk of Dr. Surendra Singh, where he discussed about polarized neutron conductivity. They have also used the same technique to actually evaluate the magnetic moment at each interface and from each layer in the multi-layer stack. And they found that some amount of C60 is actually inducing magnetic moment. That's nice, but the model was a little bit spurious because the magnetic moment was not really uniform across different interfaces. But the results were very encouraging. Now there are many other papers. I have selected again this paper where it shows something called a 4-atom hole reconstruction, because when the C60 molecule is like a football, so it will go and sit, on the ferromagnetic surface. You will have, some removal of the ferromagnetic atoms, where you will form like a sitting place for this football, and it will come there, and there will be hybridization between the carbon and the atoms of the ferromagnet, and that will induce some magnetism in carbon, and that has been theoretically and experimentally shown. This is another very nice paper from Paris, where they have shown that if you fix the ferromagnetic thickness and you have certain anisotropy, let's say it has in-plane anisotropy, and you just deposit some layers of C60 monolayer, less than monolayer of C60 in a sequential way, and they found as a function of C60 thickness, you can actually enhance the magnetic anisotropy, and you can make a spin orientation from in-plane to perpendicular anisotropy just by depositing C60 on top of this ferromagnetic cobalt. So that's remarkable because you can really now play around with anisotropy and the spin orientation condition just by depositing C60. So with this brief literature survey. There are a few other important papers. There are still a lot of open questions when we started this field something like 6-7 years back. The question is, how much thickness actually the C60 will exactly show magnetic movement? Then what are the implications of this interface on anisotropy, magnetization universal domain structure of the whole system? Then how the thickness and the choice of ferromagnet actually affects this interface? Okay. Now, is there any growth condition dependence, like if the ferromagnetic material is amorphous or polycrystalline or epitaxial, will it have any implication on this interface movement? Now, the recent questions what we are trying to address is, can you tune Jablonski-Murray interactions with C60 in a multi-layer star? And finally, as I said, C60 is expected to exhibit low spin orbit coupling, but still, can you do SOT kind of physics with C60? So let's start with polycrystalline iron films on silicon substrate. So we have prepared the samples in this spotting system, and which has also the electron beam evaporation and thermal evaporation in one chamber. So you can deposit iron film on top of the C60. Please note that the way we deposit our film, because it is with some kind of oblique angle of incidence, you induce some kind of growth induced anisotropy in the ferromagnetic films. You don't have to apply a magnetic field. So these are some cross-sectional TM images for this polycrystalline iron. You see the columnar kind of growth, and this is C60 on top of it here. And when we try to image the magnetic domains with the magneto-optic or microscope, it's a very simple technique. Already Professor Anil Kumar has discussed yesterday. It is like a simple Malus law kind of experiment where two polarizers are crossly polarized. So if you put a mirror sample, no light will be detected at the detector. However, if you put a magnetic sample, the polarization of the light will interact with the magnetization, something called Jones matrix formalism, and via this you can have a rotation of polarization that will pass through the analyzer, and you will be able to detect. Now you can use a detector, it will be simply magneto-optic or effect magnetometer, or you put a camera instead of a detector, then you can do also the magneto-optic or effect microscopy. So that means you can measure the hysteresis loop. At the same time, you can also have domain images at each magnetic field. It's like just taking pictures with your mobile phone. It's really real-time domain imaging. There are several types of MOC, and mostly we have focused in our work in this talk is longitudinal MOC, where the magnetization is in plane or magnetization is out of plane. That will be called the polar. Now let's see the magnetic domains for the single layer iron sample, and for the bilayer with iron and C60. Although the hysteresis loops look similar, coercivity slightly decreases for the bilayer, but the domain size also slightly decreases for the bilayer. That means one thing we notice that for the deposition of C60, you will have a decrease in domain size. That's one take-home message. Now let's talk about the interface evaluation of the magnetic moment via PMR. I think already Dr. Surendra has explained yesterday. It's a simple neutron polarized technique like X-ray, but as you know, neutron have magnetic moment. So you can evaluate the structural as well as magnetic information. And the procedure is very simple. You measure at the saturation. Then from that neutron data, you actually first feed the structural parameters and the magnetic moment for each layer. Then you go to the other field points in the hysteresis loop. And from there, you actually try to find out the magnetic spin orientation and the magnetic moment of each layer. So this is how you measure, and here is a polarized neutron reflectivity data for this polycrystalline iron C60 film. By fitting, it takes a lot of time though. You can evaluate the magnetic moment of the magnetic layer and also some interdiffusion. And finally, we found there is about 1 nanometer of C60 where there is no interdiffusion of iron, but you have a magnetic moment of nearly 1.4 mu per kg. So means that it has to be divided by 60 carbon atoms because C60 has 60 carbon atoms. Now you change the iron film from 3.5 to 7.5 nanometer. We see a slight enhancement of the magnetic moment and also slight enhancement of the C60 thickness, which is becoming magnetic. Here it was 1.1, here it is 1.5. Then we take another sample which is a little bit more iron thickness, 18 nanometer, and magnetic moment is close to 2 mu. So if you summarize, you see if you increase the ferromagnetic thickness, then your magnetic moment slightly increases, and your also thickness of C60 slightly increases, but it's all below kind of 2 mu Bohr and 2 nanometer of thickness. Now, what about the anisotropy? So for that, we have performed the ferromagnetic resonance, and we rotated the sample in 360 degree. So you can plot the resonance field versus the whole 2 pi angle, and you find this kind of twofold symmetry, which clearly tells that it has uniaxial anisotropy, and you can evaluate by fitting the anisotropy for the single layer, and for the bilayer we see that there is a reduction of anisotropy nearly by 50%. So this is not good, because you are actually reducing the anisotropy by depositing C60. So this is another take-home message. Now let's see what about the epitaxial iron. So previously we have discussed the polycrystalline iron, and we found the domain size decreases, which is good for technology, but the anisotropy decreases, so which is maybe not so good. Nevertheless, you have some induced magnetism in C60. Now let's talk about epitaxial iron, which is deposited on MgO001. Iron and MgO, they are very nice lattice matching, so you can actually have cubic anisotropy, and the way we are depositing our films in our chamber, if you cleverly align, you will have also a cubic and uniaxial anisotropy superimposed on each other. So we did some kind of secondary ion mass spectroscopy for some structural analysis, and we found there is maybe a little bit interdiffusion about 1 nanometer. That's kind of unavoidable. Nevertheless, we did the PNR measurements. So from the polarized neutron selectivity, we found now the induced magnetic movement in this 2 nanometer of C60. C60, please note, it was like 35 nanometer, and out of that, about 2 nanometer is actually getting a pure magnetism, and which is exhibiting a magnetic moment of nearly 3 mu Bohr. This is the highest magnetic moment reported so far induced in C60, and that's really nice. It shows that when you have epitaxial ferromagnetic films, you can induce more magnetism or more magnetic movement in C60. So this work was highlighted in the emergent neutron reactor annual report. Now let's talk about the magnetization reversal. Because of limited time, I will not go into the details, but quickly you can see the single layer the iron film exhibit this kind of magnetic loops when you vary the angle of magnetic field with respect to the z-axis. Now you do the same for the bilayer iron C60 on MgO, and you see that at some angles the hysteresis looks completely different as compared to the reference single layer. That means your spintronics is actually playing a major role. Obviously, we need time to explain, but you can go to these papers, and in terms of this energy diagram, looking the anisotropy directions, you can explain this magnetization reversal. Now let's talk about quickly the domain images. Again, single layer, I just choose one particular angle, but you can actually, we have shown a lot of angles, and due to time restriction, I'm not going into all the details. So in this representative angle, you see for the single layer, you have this kind of hysteresis loop, and you have this kind of stripe domains having some 90-degree reversal. But for the bilayer sample, you see very complicated reversal because of the superposition of anisotropies from this spintronics and the ferromagnetic layer, and your domain structure also now is different for the single layer. So that clearly tells that the spintronics can strongly modify your magnetization reversal and magnetic domain structure. Now let's talk about the anisotropy. So you see here that the anisotropy for the epitaxial field actually strongly getting enhanced by 2 order. Please note down for the polycrystalline films, the anisotropy for the bilayer was actually almost 50% reduced. But here you are enhancing by 2 order. We are trying to understand that. And now quickly I will just talk about polycrystalline cobalt. We have shown about the epitaxial iron and polycrystalline iron. Polycrystalline cobalt, we found that the domain size actually increases, which is not so interesting for technological point of view, and anisotropy is slightly like 20-30% getting enhanced. So this is what we see for the polycrystalline and epitaxial iron and cobalt. Now let's talk about amorphous. And cobalt iron boron is a very popular material for spintronics applications. It is amorphous, it has very low damping, it is very easy to grow material. So we have tried to also explore the cobalt iron boron C60. Recently we published this paper where we saw that you can enhance anisotropy by depositing C60 on cobalt iron boron. That means the spin interface is helping, and plus there is no change of domain structure. So it's very interesting that for the polycrystalline iron, the domain size was getting reduced. For polycrystalline cobalt, domain size was getting enhanced. But for the amorphous cobalt iron, the domain size is almost same with or without C60. Okay, now I will quickly go to the perpendicular systems. In the beginning, I have shown results for all these iron cobalt films. They are deposited on as in-plane anisotropy. Here, this is ultra thin cobalt like 0.8 nanometer, and we have taken a platinum cobalt system. And here we saw without C60, you have very big characteristic bubble domains. But when you deposit C60, you make a significant domain engineering. That's very interesting, for technological application. And we have also shown that the relaxation dynamics getting faster for the C60 case, and the measurements are performed like you go to the negative saturation, you bring to somehow reversal field, and you fix it, and you just let the magnetization relax over time under thermal and Zeeman energy. And you get the images, and you can take the average intensity, you plot it over time, and you fit it with this kind of exponential behavior. And most importantly, we are looking at the relaxation time tau. For platinum, cobalt platinum, we get something like 5 seconds. But for the C60 interface sample, we are getting the relaxation time nearly 3 seconds. So it is getting faster. The less relaxation time means the system is faster, which is good for future technological application probably. And we have done some DFT calculation with Dr. Ehsan Ali, which shows that you have this, hybridization and interface, and depending on the type of hybridization or bonding, you can have enhancement of anisotropy, and that's probably the origin of the reduction of domains. Now, quickly, I will talk about the DMI physics with the C60. You can also take palladium cobalt, just like platinum cobalt, where you can enhance the, or you can have a perpendicular magnetic anisotropy. Now we are putting C60, and we are trying to see how you can tune the anisotropy and the DMI. So for that, before that, first we have measured the domain wall velocity in such kind of experiments. We modified our core microscopy a bit, and we follow this procedure. You saturate, then you nucleate, and then finally you propagate the domains, and you see how much elongation it has made. And if you divide the time it takes, then you can actually find out the velocity. And then here I plot quickly the velocity for the 0 nanometer. That means it's simply palladium, cobalt, palladium sample. And with C60, that means it's palladium, cobalt, C60 palladium, and various thickness of C60. And here we see that, I don't have much time. Again, you can fit this creep law, but that the domain wall velocity is, faster for the C60 sample. So that's actually a good thing that C60 is helping. And now talking about DMI, already Professor Seki explained yesterday the antisymmetric exchange, which is like SI cross SJ, and this D is the DMI constant. So it is basically kind of, chiral structure at the interface between heavy metals and ferromagnetic elements. So you can also follow the similar type of domain wall velocity measurements, but here you have to also apply an in-plane field. And then you can evaluate the DMI. The procedure is similar, because if you have some kind of DMI, your domain wall propagation will be asymmetric. In one direction, it will be more. In another direction, it will be a little bit less. Now, if you plot the right velocity and the left velocity as a function of the field, you will get this kind of behavior if you have DMI. And if you have no DMI, it will be symmetric around the origin. So from that, you can calculate actually the DMI field, and you can use this formula to finally calculate the DMI energy. We have done that for this C60 0 nanometer, 0.8 and 1.6 nanometer. And we found that if you have 0 nanometer, you have very little domain this DMI energy. But when you have C60, you can enhance to quite a bit of high. So basically, if I show this picture, it will be clear that for the palladium cobalt, we find it's very standard. And we found it's about 0.35 millijoule per meter square. For cobalt C60, so that means you see there is almost no DMI, it's minus 90 microjoule. However, if you take platinum, a palladium cobalt C60, then you see that the DMI is getting more than simple palladium cobalt. So the C60 is actually kind of helping. So it is contributing somehow to the DMI. That means it has also some amount of spin orbit coupling. Now, quickly in last 1 minute, I will just show that if you can expect that there can be spin orbit coupling in the C60, which should not have actually spin orbit coupling, then you can expect to observe this kind of spin Hall effect. So I will not go into this introduction. I can skip it. Basically, you have the spin Hall effect. You apply a charge current. You have spin imbalance. You can create a spin current. Now, just imagine you have the spin current. You pass it through the sample. You will have charge accumulation, and you can get a Hall voltage, which you call the inverse spin Hall effect. And there has been some reports in literature where it has been told that the C60, because it has a curvature, that can actually lead to enhancement of spin orbit coupling. Of course, the details is not explored, and I think now we have to look at that aspect. But nevertheless, people have also observed some amount of spin pumping in this kind of organic semiconductor nickel iron using some special technique. Or here they took platinum next to C60 to enhance the effect. And here in our case, we have not put any platinum. We have just taken cobalt iron boron and C60, and we have observed clear spin pumping and ISHE signals. We have done the analysis, and this is under review. And we have taken systematic analysis. The message is very nice that you can also expect high spin orbit coupling from C60-like compounds where no spin orbit coupling is expected, because you are depositing as a thin film, and this curvature and this kind of spinterface is actually enhancing. Now, question is how much the spinterface is contributing to this spin orbit coupling, and how much is the curvature is contributing. Those kind of physics this has to be disentangled in future. So with this small note, I will like to stop now and take your questions. Thank you very much for your kind attention.
Thank you very much, Spankal. So that is a very exciting talk. So from audience, do you have any question or comment? So this talk opens a question and answer. Any question?
Seems no questions. I'm happy to answer if there are questions.
All right, I have one question.
Yeah, please.
So you maybe you mentioned, so the order of stacking is very important to prepare this heterostructure consisting of organic semiconductor and ferromagnetic metal. If you invert the order of the stacking, for example, organic semiconductor and ferromagnetic layer, or ferromagnetic layer and organic semiconductor, did you see any change in the efficiency of spin Hall effect or something like that?
I think this is an excellent question. Okay, so the point, this is something in our plan to do. For instance, if you look, I think this one. So cobalt iron boron is having this amorphous nature. So, but still, if you deposit on top of C60, because you can imagine C60s are like big footballs. Okay, so when you deposit cobalt iron boron on top of it, then I think cobalt iron boron will go more inside the C60. So you will have a lot of interdiffusion. Okay, so but this is something to be looked at, how it will affect. But for cobalt iron boron, it's not a problem. But if you are thinking about in epitaxial film, like or in polycrystalline iron or cobalt, probably the things will be different, because the growth will be much different on the substrate directly rather than on C60. And nevertheless, we put also sometimes little bit tantalum before, very thin tantalum for a better growth. And now on C60, this is a good question. We have to answer that. This is already in our mind, and we will probably find the answer.
Okay, thanks. Any other question? Okay, another question.
Yeah.
So you showed the existence of the spin interface between organic semiconductor and ferromagnetic layer. Is that good for spin injection or bad for spin injection if you have the spin interface?
Yes, I mean we have not started this spin transport or basically magneto transport or so, but there are many groups. Actually, it all started with the spin transport study, and they claim that you can observe a reasonable amount of magneto like TMR with this organic semiconductor as a special layer. So actually, majority of the research on organic spintronics focuses on the TMR part. I think our group is something we are looking at this domain reversal a little bit different to what others are doing. But this is a good question. So far, whatever knowledge we have, it seems it is helping. But obviously, we need to look, because there is a plethora of organic materials, and the C60. Then there are some other compounds like group-brin, LQ3. There are a few compounds which has been taken rigorously by different groups, and it seems this interface kind of helps. Now, why? I mean, this research field is very new. It's less than 10 years, and very few groups are working. So more theoretical support is probably needed to understand how this spin transport occurs and how this spin interface is adding to it, or what is its actually role. So it's a very good question.
Okay, so the question from the Naha Kapila Sharma.
Yeah. Good morning, sir.
Yes, please.
So very nice talk. I have one question actually, sir. I have studied smaller clusters also, not only C60 but C40, C28. Those cages are also there.
Oh yeah.
So as you are saying that this SOC depends upon the curvature of the cluster. So can we expect, like, if we are using some other clusters, so SOC will decrease or whether it will increase as it is depending on the curvature?
Yeah, I mean, it's a wonderful question. We have not done that with other structures, but I think there is a paper in Journal of Applied Physics, if I recall. They have taken C70 and C84. I'm not sure if they have taken something C40 or something. So I think this, as I said, they have just reported something is happening, but detailed investigation is missing. So this is also in our to-do list. Maybe we can talk about it, and I'm happy to discuss this maybe today in the poster session. But very good question. I think, to my knowledge, this kind of clear investigation is not done.
Fine.
Yeah, thank you.
All right, so we have another question in the chat box, but maybe the time is go out. So,
yes.
So please, discuss at the poster session.
Yes.
Later.
Yeah.
Okay. And so, Tsubankao, so I should give you the moment, something like digital.
Oh, okay.
Yes,
This
that's
is
right.
my group thing. Okay. It's a bit absurd, but yeah. Thank you.
Yeah, this is for you. So
thank you.
Thank you very much for your nice talk.
Thank you.
Thank you. Okay, yes. So we should move to the next talk. And the next talk will be given by Professor Keita Ito in Tohoku University. Actually, he is my colleague. And so he will make a presentation about the fabricating L10 ordered iron nickel films by denitriding iron nickel nitride films.
Okay.
Can
you see?
Okay, I can hear you.
Okay.
And screen sharing is fine. So please start.
Okay, thank you. So thank you very much for your kind introduction. So thank you very much for giving this special opportunity. So I'm Keita Ito from Tohoku University, and today I will talk about fabricating L10 ordered iron nickel films by denitriding iron nickel nitride films. So this is an outline of today's my talk. So first I will talk about the features of L10 ordered iron nickel, and then I will show you the result of fabrication of 100 oriented L10 ordered iron nickel films by denitriding 100 ordered iron nickel nitride films. And finally, I will show you the result on the 110 oriented films. Okay, let me start with the background of this work. So, so ferromatic material with large uniaxial magnetic anisotropy energy Ku is required in order to realize next generation high performance motor or magnetic recording media, as shown here. So this table shows the typical large Ku materials. And so in most of these materials, so the noble elements such as rare earth or precious metals, so such as platinum, are contained in these materials, in these large Ku materials. So a noble element-free large Ku materials is required to achieve a sustainable society. So I have focused on the L10 ordered iron nickel. So the structure of L10 iron nickel is as shown here. And this is a face-centered tetragonal structure with alternate stacking of nickel and iron layer along the C-axis direction. So this material is contained in iron meteorite. And so this is a rare element-free materials, so large saturation magnetization, high corrosion resistance, high Q temperature, and large Ku is reported. So we consider this material is promising for noble element-free large Ku material. However, so there are several problems. So this figure shows the iron nickel binary alloy phase diagram, and the L10 region is shown here. So from this figure, so we can see the low order disorder transition temperature of this material is about 320 degrees Celsius. So below such a low temperature, so diffusion speed of iron and nickel is quite slow. So this means it is very difficult to obtain L10 ordered iron nickel, L10 phase by annealing so random iron nickel alloy. So because the diffusion speed is very small, very slow. So it is difficult to fabricate this phase. But there are several reports on the fabrication of L10 iron nickel. So this is a result of our groups, and so this is a result of alternate monatomic layer deposition by molecular film epitaxy, as shown here. So by this method, we obtained single crystalline 001 oriented L10 iron nickel films like this. And this figure shows a result of a relationship between a long range degree of order of iron nickel and uniaxial magnetic anisotropy. So from this figure, so we have obtained so about Ku of 0.7 megajoule per cubic meter when S equals 0.5. And this is a result of film forms. And there are several reports on the fabrication of bulk form sample. So the top figure shows the result of severe plastic deformation technique and heat treatment. And we can see the diffraction from L10 ordered phase, but the degree of order of this sample is very small. And the bottom shows the Xrd patterns of L10 ordered iron nickel fabricated by annealing to this amorphous alloy. So we can see the superlattice diffraction peaks, but volume fraction of L10 phase is very small. So problem is so degree of order or volume fraction of L10 phase is very low. But recently, so new method to fabricate L10 ordered iron nickel is developed by Denso Corporation in Japan. So this is a so-called top tactic extraction of nitrogen atoms from iron nickel nitride. So this figure shows a brief explanation of this denitriding method. First, so random iron nickel alloy is nitriding by annealing in NH3 gas atmosphere, and we can get we obtained iron nickel nitride like this. So structure is of this material is very similar to that of L10 ordered iron nickel. And denitriding this iron nickel nitride, we by annealing in hydrogen gas, we obtained L1. We can obtain L10 ordered iron nickel. So by using this method, so L10 ordered iron nickel powder with high degree of order, about 0.71, was successfully formed. But single crystalline L10 iron nickel is required to evaluate exact Ku value. So objective of our research is the growth of single crystalline epitaxial iron nickel nitride films and fabrication of L10 ordered iron nickel films with large degree of order and large uniaxial magnetic anisotropy by topolactic extraction of nitrogen atoms from this antiferromantic iron nickel nitride. So, okay, here I will show the result of fabrication of 100 oriented L10 iron nickel films by denitriding 100 oriented iron nickel nitride films. So iron nickel nitride films were grown on STO001 substrate by molecular beam epitaxy, supplying iron, nickel, and radio frequency nitrogen plasma. So the details of growth conditions and denitriding conditions are shown here. And we have changed the growth temperature growth temperature of iron nickel nitride films as 200 degrees Celsius, 250 degrees Celsius, and 350 degrees Celsius. So grown layers were characterized by X-ray diffraction using conventional kappa K alpha radiation source and synchrotron radiation. So, and the magnetic properties were characterized by a magnetization curve measurement and magnetic torque measurement. And structure was confirmed by cross-sectional TEM measurement. So first, I will show the structure of iron nickel nitride films grown on STO001 substrate. So the left figure shows the Xrd patterns of these three samples. And so in the out of plane Xrd patterns, we can see the diffraction peaks from iron nickel nitride 200 for all these samples. And so in the in-plane Xrd pattern, we can see the diffraction from 001, 200, and 002. So from these results, we confirm the structure of this sample as shown here. So this means that the iron nickel nitride films with A-axis perpendicular to the film plane were epitaxially grown on STO001 substrate with this epitaxial relationship. So this means that there are two variants, so variant A and variant B, with in-plane orthogonal C-axis were formed. So C-axis so there are the two C-axis. To influence C-axis. And next, after denitriding these samples, we performed in-plane anomalous Xrd measurement in the synchrotron radiation facility Spring 8 in Japan. So this figure shows the result of anomalous Xrd measurement, and the left figure shows the superlattice diffraction, and the right shows the fundamental diffraction. So we use X-ray wavelength of about 0.17 nanometer. So which corresponds to the absorption edge of iron. So iron KH energy. So from this result, the superlattice diffraction of L10 ordered iron nickel 001 is obtained for when the gross temperature was 350 degrees Celsius. And from these results, we have calculated the degree of order of this sample, and the value was S equals 0.87. So this value is very large. Next, I will show the magnetic properties of the samples. So this figure shows the magnetization curves of the samples. And in the perpendicular magnetization curves, so the saturation field was increased with increasing the gross temperature of ironical nitride layer. And this value is obviously larger than that for the demagnetization field of L10 ordered iron nickel. So this means so the Ku is induced in the in-plane direction of the film like this. So in order to evaluate exact Ku value, so we perform the magnetic torque measurement for these samples and using with so-called 45-degree torque method. So due to the time limitation, I will skip the details of the analysis. But anyway, so we achieved Ku of 0.59 megajoule per cubic meter with so S equals 0.87 as shown here. However, so this Ku value, so this 0.59 megajoule per cubic meter is smaller than that was expected from the previous study on the C-axis-oriented epitaxial iron nickel nitride films. So this plot is this result in the denitriding iron nickel nitride 100 films. So from the previous report, we have expected about 1.2 megajoule per cubic meter when S equals 0.87, as shown here. But our sample, Ku of our sample is very small. So we consider possible origin of this small macroscopic Ku value of this sample. So the Hertzer reported that in nanocrystalline ferromagnetic films, the macroscopic Ku value is averaged and becomes smaller than Ku of each crystal grain when the crystal grain size is smaller than the exchange length, as shown here. So our structure of our sample is not nanocrystalline polycrystal films, but structure is very similar to that of the nanocrystalline film due to these orthogonal in-plane C-axis. So we estimate the exchange length of L10 ordered iron nickel as shown here, and it's about a few nanometer. So this means that if the variant size of our sample is a few nanometer, the actual Ku is much larger than the obtained macroscopic Ku value. So we confirm the variant size of this sample by using TEM observation. So the left figure shows the cross-sectional TEM images of the sample, and the right figure shows the FFT images of this area, so A, B, C, D. And so from FFT, this length is about 5 nanometer, and we change the observation area from A to B. So the position of superlattice refraction spot is changed from this. So this means the variant size were roughly estimated to be a few nanometer from this TEM observation. So, and according to discussion from the previous slide, so the actual Ku of each variant is much larger than the 0.59 megajoule per cubic meter. So this is a brief summary on the result of L10 ordered iron nickel 100 oriented films. So the S equals 0.87 and Ku of 0.59 megajoule per cubic meter were realized. However, this Ku value is smaller than that's expected from the previous study. So the origin of the small Ku is that the microstructure having 2 nanometer sized variant with the impedance shear orthogonal to each other. So the actual Ku of each variant is much larger than this value. So this means that in order to evaluate its exact Ku value, we need to fabricate variant-free L10 ordered iron nickel films by denitriding method. So next I will try. I will show the result of variant-free fabrication of variant-free iron nickel nitride 110 films and denitriding. So this one. So the 100 oriented iron nickel nitride films were fabricated by RF assisted molecular beam epitaxy on the LAO 110 substrate. So the details of growth conditions and denitriding conditions are shown here. And the growth temperature was changed like this. And so denitriding temperature and denitriding duration time is also changed. End-grown films were characterized by this method. Okay, first I will show you the structure of 110 oriented iron nickel nitride films grown on LAO 110 substrate. So this figure shows the Xrd patterns of the samples. And we have changed growth temperature as shown here. And so the result is a single phase 110 oriented iron nickel nitride film was successfully fabricated when the growth temperature was 350 degrees C. And the degree of order of nitrogen atoms are calculated to 0.75. Next, I will show you the result of Xrd pattern after denitriding this 110 oriented iron nickel nitride films. So we have changed the growth temperature and duration time, and finally, so variant-free L10 ordered 110 oriented films is obtained when the denitriding temperature was 200 degrees Celsius and duration time was 2 hours. Okay, so next I will show the result of in-plane anomalous Xrd patterns and in-plane magnetization curves of this 110 oriented L10 iron nickel films. So by anomalous Xrd measurements, we obtained 001 superlattice peak and 002 fundamental peaks. And so Ku value, S was calculated to be 0.22 from this result. So this value is very small. And so this figure shows the in-plane magnetization curves of the sample. And red curve shows the magnetization curves when the magnetic field is applied in-plane shear axis direction. And the blue one shows the magnetization curve when the magnetic field is applied perpendicular to the in-plane shear axis. So from this result, we have calculated that the Ku value is about 0.3 megajoule per cubic meter. So this value is not so large. So in order to increase this small S value and Ku values, we performed additional annealing to this as-grown iron nickel nitride films under the atmosphere of NH3. So the top figure shows the Xrd patterns of the as-grown films, and the degree of order was 0.82. But after additional annealing in the NH3 atmosphere, so the diffraction peaks of iron nickel nitride become sharp, and so degree of order is improved from 0.82 to 0.92. So after denitriding these samples, we performed anomalous Xrd measurement and in-plane magnetization measurement. in-plane magnetization curves were measured. So the result is as shown here. So S equals 0.45 and Ku was 0.55 megajoule per cubic meter. So this means that the Ku value was improved. Ku and S was improved by annealing in NH3 to iron-nickel nitride. So finally, I will show the comparison with other orientations. So this figure shows the relationship between S and Ku of L10 ordered iron-nickel films. And so the red dot shows the result of 110 oriented films fabricated by denitriding method. And the white one shows the 001 oriented films fabricated by alternating deposition of iron and nickel layer by molecular beam epitaxy. And the blue one shows the result of 100 oriented films fabricated by denitriding. So from these results, so the 110 oriented film without variance shows a larger Ku than that of the 100 oriented film with variant. And the similar value with that of the 001 oriented films grown by alternate deposition. So this means that the larger Ku will be realized by the further optimization of the growth conditions and the denitriding condition. So let me summarize my talk. So the variant-free iron-nickel nitride 110 films were grown on LAO 110 substrates at growth temperature of 350 degrees Celsius. And so 110 oriented L10 iron nickel films were obtained by denitriding these epitaxial iron nickel nitride films, and we obtained this Ku value and S value. However, so this value was very small. So the S and K value was of the L10 iron nickel films were improved by annealing iron nickel nitride in ammonia gas and denitriding. So, and we obtained Ku of 0.55 megajoule per cubic meter and S equals 0.45. So the K value of the L10 iron nickel 110 films fabricated by denitriding and those of the films grown by the alternate deposition were almost the same range. So the larger Ku will be realized by further optimization of the growth and denitriding conditions. So that's all. So thank you very much for your kind attention.
Thank you very much. Thank you very much for a nice talk. So any question or comment from audience? Yes, please, Yoshimura-san.
Hi, so I'm Satoru Yoshimura from Oxide University, Japan. Thank you very much for your nice talk. I have a question about the order parameter between iron nickel nitride and iron nickel.
Yeah.
So I think so no data, but yeah. Okay. In the case of the iron nickel nitride, the order parameter is very high, 0.7,
Yes.
0.8.
Yeah.
So after that, so you
It's a decrease. Yeah.
Yeah. So if you can reduce the remove the nitrogen atom from the sample, the order parameter becomes same, I think. So why the order parameter decrease?
Maybe so. So this is a very big problem for us. So maybe so. So when the nitrogen atoms was released from this iron nickel nitride, so this ordered structure is also little bit also destroyed. Maybe so. But so from this is the first report from Denso Corporation, and they first obtained the very perfect order to iron nickel nitride. But after denitriding, so S equal reduced to the 0.71. So how to say? So yes, I don't I don't know how to how to prevent this reduction of S. So this is a future. Yes, this is a very big problem for us. Yeah.
Okay, so this phenomenon is both case for your film and
Yeah.
this powder.
Yeah.
Okay, so other mechanism about the reduction of the order parameter. Not only the film but also the powder.
Yeah, both in both cases, so the S is reduced. Yeah.
Okay, thank you very much.
Thank you for question. Any other question?
Hello, sir.
Yeah.
Is I'm audible? Is I'm audible, sir?
Sorry, what? Pardon?
Is I'm audible, sir?
Mori?
This is Harshvardhan, sir. Thank you for very nice talk. Sir, I am actually interested in the way you have calculated these Ku values from the hysteresis loop.
Yeah. From we have calculated Ku from this area.
Yes.
Yeah.
So how you have calculated these Ku values from this loop?
Just so we have calculated from this area, so surrounded by this red line and blue line.
Okay.
This is corresponding to the Ku. Yeah.
Okay. This area is actually equals to Ku.
Yeah. Because both is in plane magnetization curve. Yeah.
Okay.
But the direction is different. Yeah.
Thank you very much, sir.
Yeah.
Box, we have another question. Are you working in recording media application?
Recording media application means such as hard disk drive, or maybe, but our purpose of this actually I don't try to fabricate this recording media application. We how to say we want to apply this material to permanent magnet. Yeah.
That means the major purpose is for application to the permanent magnet.
Yeah,
But
layer 3.
I guess so. We have a chance to apply this material to the recording media also.
Yes,
if we get the very high
perpendicular. Yeah. So
perpendicular
in this, so. But now, so we have not achieved the 001 oriented iron nickel nitride films fabricated by denitriding method. So this is a future plan.
All right. Any other question? If not, thank you very much, Ito-san. Nice talk.
So thank you very much.
Let's move to the next talk. Oh, sorry, I forgot. So this is a memento for you.
Oh, thank you very
your
much.
Talk. Thank you so much.
Thank you so much.
And just a moment. All right. And next talk will be given by Dr. Anjana Dogla from NPL India.
Yeah.
Anjana.
Yeah, I'm there. Can you hear me?
Yes, I can hear you.
Okay, fine.
Please share your screen.
Yeah, just a moment.
Yes. Yes, now I can see your screen, and please share your PPT or PDF, or I'm not sure.
Yeah. Okay, can you see that?
Just a moment. It does not work.
No?
No. In my screen, I'm not sure this is my problem or not. Your sharing is now stopped, I think. Okay, could you please escape from the screen sharing once and please try again?
Okay, fine. Is it visible now?
No.
No, Anjana, I think it is not working. You need to stop sharing and start sharing again.
Okay. Sharing.
And do you use 2 monitors or just 1 monitor?
Only one.
Okay. Then when you share, please share the full screen. Sometimes if you have many windows open in the computer, it will ask to share only, let's say you only choose one, then it creates problem. Please share the whole screen.
Okay, fine.
Yeah.
I am sharing actually full screen only.
Okay.
First, please open your PPT file.
Yes.
And then start the screen sharing.
Okay. Just a minute. Is it visible now?
Yes.
Yes,
okay.
Perfect.
Now you go to the full screen mode.
Okay.
Thank you.
Yeah, it's fine now?
Yes, very fine.
Okay.
Okay. So next talk will be given by Anjana, and she will talk about the two-day characteristic difference between stoichiometric LSO, STO, and non-stoichiometric CTO, STO. So please start.
Thank you, Professor Seki. And first of all, I would like to thank the organizers to give me this opportunity to present my work. So myself, Anjana from NPL, National Physical Laboratory. This is the building which is at the background which I have put. And it is located in New Delhi, the capital of India. So the topic of my presentation is two-dimensional electron gas. At the two interfaces I will be talking about. One is lanthanum scandium oxide at STO, that is strontium titanate, and other one is calcium tantalate, TaO. It's not the stoichiometry, that's why I have put X and Y on STO. So this basically work is carried by us, and we have many people who are involved in this work. And the person who has mainly worked is Sumit Kumar. He is my PhD student. So this is his PhD work. Okay. And yeah. Coming to the interfaces, everybody, like since yesterday we are talking about interface, so we all are familiar with the interface now. So it is just one material on top of that. When we deposit another material, it comes out to be the interface at the center, like the figure represent. One is the oxide is substrate, and top of that when I am growing thin film, and at the interface, that interface is the basic interest behind our studies. So as one of the Nobel laureate Cromer has said often, it may be said that the interface is a device. So if you see this particular material, since the discovery, I think in the 2004, and then later on, many people have talked about these material. When you talk about SrTiO3 and lanthanum aluminate, LaAlO3. So when you deposit AlO3 on SrTiO3, it makes an interface, and surprisingly at interface you observe the two-dimensional electron gas. And this electron gas, which is being originated at the interface, will lead to many properties or unique properties. So we will just look into this. So to start with, I will just tell that STO as well as LAO, both are insulators and both are non-magnetic material. Okay. And coming to the interest of two-dimensional electron gas, to define, let us understand it can be two-dimensional electron gas, or it can be two-dimensional whole gas. It can be either, depending on the materials. So it is basically the accumulation of electrons which are free to move in X and Y direction, but it is confined in the Z direction. So that's the name defined. Okay. So what is the interest behind these kind of materials or two dead materials? So because it is having high electron mobility, and at low temperatures and with high quality material, electron can travel many microns without scattering of impurities. That is why the interest comes into these materials, and this kind of materials leads to the like interesting physics such as quantum Hall effect and some other applications as well. So just to start with, this is recent photograph which is taken by the drone during the Science Day, which we celebrate on 28th of February. So this is the main building which is being visible, and we were celebrating the Science Day on that day. So I was just telling, like, there is one substrate and the thin film we are depositing and interface. So it is just if we understand, like, this bottom layer, if you see these three layers of in building also we have three layers. Okay, three layers in sense, the bottom we can say substrate, and in the middle we have the interface, and the top we have the film which we are depositing. And now like, I have considered the thin films as scientists, which we people work, or the other students also work. And now the scientists think that it is our property or whatever kind of work we are doing, but it is basically how your work is leading to and where it leads. It basically depends on the interface which is being made with the substrate, that is the director of the institute. Okay, so what kind of facilities and how we are being entertained with the facilities. So these kind of things, like, and similarly for students also, we can just understand how you make the interface with your guide or the boss. So that kind of, like, whether you get the two-dimensional electron gas or some unique thesis in when you work. So just a simple example I was trying to give. And coming to this, I mean, why these are interesting, like the discovery was in the 2004 when Huang et al., they have published one paper in Nature where they show that ALO3 when grown on STO, they shows the conducting, and which are very much insulating as per in the nature, but because of the emergence of this two deck, the conducting nature has been observed. And also they were able to, I mean, the next group in the year 2007, Brinkman in the Nature Materials, they have published. So they could show the magnetoresistance behavior as well. So, and the most surprising result was the superconductivity in these kind of material, where the materials in the pristine form, it is insulating. However, when they comes in this form, they are able to show the superconductivity, but at very low temperature, that is in millikelvin range. So you can see the range is almost about like 260, 200 to 260 millikelvin range, where you see the transition of superconductivity from I mean, normal metal. And then whatever properties people are talking about, whether they are representing this MR or superconductivity or any kind of conductivity, it always depends on the critical thickness. Critical thickness, I mean to say that at the thickness below which you don't find any kind of conductivity or any kind of these properties. However, when we go beyond this thickness, you will able to see that these kind of properties. So that we call it as a critical thickness. Like these materials, if you see this bottom graph, right hand side, at 4 unit cell, okay, you can say 1 unit cell is equivalent to 4 angstrom. So we can just calculate it. If I'm saying 4 unit cell is almost 40 angstrom or 4 nanometer, I can say. So beyond that thickness, we are able to, people are able to see the these kind of unique properties. And surprisingly, when below this critical thickness, that is 4 unit cell, below this, if we people are applying this gate voltage, then they can also modulate the conductivity in these kind of like 3 unit cell and 2 unit cell. Like for the left hand side, the bottom figure, you can say the conductivity is modulated with the application of gate voltage. So there are many models actually which are being, one slide I have missed actually. Okay, anyhow, no matter. So why these properties are being observed. So people have talked about many mechanism. So people have talked about there is a possibility when you are growing the thin film on this kind of substrate, then there is a chances that because intermixing at the interface. So when you are in, there is happening of intermixing, then there is no LO ALO3, rather than it is LO STO. The SR is and titanium are mixed with this LO. So which gives to rise to the conductivity. That kind of mechanism have people talked about, and they have also talked about the oxygen vacancies. That there is a possibility, because when you are making the film, then you are annealing the substrate, then there is a possibility that you are creating oxygen vacancies in these materials, and these oxygen vacancies or any kind of defects are leading to the conductivity in these kind of materials. And apart from that, people have also talked about the strain. If there is a mismatching of the substrate and the film, then you can see these kind of effects. So different kind of theories have been given, but the most successful theory which has been people have been talked about, that is polar catastrophe model. So polar catastrophe model is nothing but, if you remember the superconductors, when we say like YBCO, the people have talked about, they have the layered structure. Similarly, if you see the left hand side figure, let us say STO, SRTiO3. So SRTiO3, we are saying it is in the layer form. Like the first layer is SR2 plus O2 minus. The next layer is Ti4 plus O2 O minus. So in this way, and similarly, LO on top of that, it is also in the layered form. Okay. So it is La3 plus O2 minus. If you see the charge neutrality kind of thing, if you talked about, then you can see that it's a 0, and here is +1 plus minus charge is on the these kind of layers. So what is happening basically, when there is a kind of electric potential which is induced because of this alternating charge layers which you are seeing. So what is happening, that is there is a divergence. Okay. So how to avoid this divergence? So that this divergence is being avoided if half of the electron is being transferred from, let us say, this LAO layer to the Ti. Okay, so now the valence state of Ti has been changed. So in that way, the divergence has been avoided, and the emergence of, you can say, the reconstruction, the layer reconstruction has been happened. So most of the people who have who are working or worked on these kind of systems, they have explained this kind of mechanism in these 2-deck heterostructures. So till now, the people have talked about this oxygen vacancy, etc., etc. And very recent in 2015, one of the group Chen et al. They have published in Nano Letters. They have talked about the strain-induced polarization. Just to remind, these kind of structures, earlier structure which I am talking about, LAO, ALO2, TiO2 structures, or you can replace LAO with the LATiO3 or LAVO3, kind of many kind of families has been discovered. So all are basically polar non-polar. If you see, when I'm saying polar non-polar structure, by this structure which I'm explaining in the left side of the figure. Okay. However, in 2015, they have represented that CZO on STO. This is non-polar, non-polar. So now the non-polar thing has come. Then polar catastrophe model almost fails here. So then they have talked about the strain-driven polarization in these kind of material. And the critical thickness, which was 4 unit cell earlier in the systems, which has been changed to 8 unit cell. That is, below 8 unit cell they were insulating, however above 8 unit cell they were conducting. And the highest mobility in these kind of systems has been achieved at 2 Kelvin, basically, that is 60,000 centimeter square per volt second. So this is the highest in the oxide structures. Okay. So why we need such kind of oxide interfaces? People might be aware that already we have a lot of market for the semiconductor heterostructures, where they have a wealth of devices, PN junction, Schottky diodes, and all these kind of things, the high mobility transistors, and they are all based on two-dimensional electron gas at the interface. However, when we talk about oxide interfaces, so why the interest has been come, because the kind of properties which I was telling, whether it is superconducting, whether it is you shine a light on these kind of materials, then you change, you modulate the conductivity at the interface. So these kind of properties are not being observed in the semiconductor heterostructure. However, they are into the oxide interfaces. So these kind of novel physical properties like superconductivity or magnetism or the light effect kind of thing on these material, they give a kind of chance to the oxide interfaces to come up into the applications. So that is why the interest has been come up. And moreover, oxide 2-deck has much narrower distribution of electrons within a few nanometer compared to the semiconductor 2-deck. So which enables that electronic circuits can be within the nanoscale, that is the 2 nanometer wide conducting path, okay, which will be equivalent to the nanotubes. So that is the attraction behind these kind of two-dimensional electron gas systems in these oxide systems. As I said that these, the beauty of these kind of materials, one of the paper published in 2013 in Advanced Material, these kind of systems can be modulated by various external signals such as light, which is, we can say, photoconductivity, then electric field, and you can also modulate with application of magnetic field and the pressure. So this basically brings the increase the functionality of these kind of layered structures. So coming to our work, so we have chosen two systems, that is LA-SCO3 on STO and CA-TO2-06 on STO. So basic interest was behind these systems. First of all, as I mentioned that the mechanism is still a big thing to be inquired. And also the systems like LAO-STO or any other system which has been discovered till date have very low mobility and high carrier concentration. So when we talk about quantum phenomenon, because since we are talking about two-dimensional electron gas, so this this basically stops the oxide involvement in the applications. So that is why there is a need to look for new systems or various different mechanism into these systems. So that is why we have chosen some systems. So coming to LA-SCO3, SRTIO3, the first system. This is the basic PLD setup, the pulse laser deposition, all the films which we make with the laser. The sixth number is the laser, and this is small chamber in front of the laser. And we have the read gun. Read gun is this reflection high energy electron diffraction gun, which generally measure the diffraction pattern during the deposition, in situ deposition. So this is a small chamber in between. I don't know. So, and the computer is basically for the kind of whatever we see, the diffraction pattern in this camera. The 3 number is the camera. So that is being visible in this computer. So the laser which we are using, this is KRF laser with the wavelength of 248 nanometer. And coming to the growth sequence, how we have grown. So target which we prepare is LSO material pellet, which we generally prepare by solid state technique. And the substrate which we have taken, SRTIO3, but it is not pure SRTIO3, it is terminated, TiO2 terminated, which means we have etched the surface with the HF solutions. So purpose of the HF solution to terminate this, because as I said in the earlier graph, earlier slides, that we want the top layer, because this is a layer structure. So we want the TiO layer has to be topmost, and on top of that layer, we need to grow the LAO-STO. Okay, so LAO will come on TiO2. So that is why the purpose to terminate the TiO2 termination is important. And this is a flow chart and oxygen pressure 1, 2, 3 SSEM, which we have used while growing the films, and the target to substrate distance, which is very much important in these kind of PLD growth. This is 4.9 centimeter, and the pressure while we grow the film, it is 1 to 10 raised to -4 millibar. And the laser energy that we have used, this is 1 joule per centimeter square, and the frequency was at 1 hertz. So coming to the results, let us say the A figure towards my left top figure. If you see some kind of oscillations we observe. So what these oscillations are representing? So let us start with the blue oscillation. So if you see one oscillation is going down and up. So one oscillation is representing the 1 unit cell growth of my material, whatever I am growing. Let us say I am growing LaSCO3. So one layer of, 1 unit cell of LSO I have grown. Now here you see there are 4 oscillations. So which represent I have grown 4 unit cell thickness SCO on SRTiO3. Similarly, if I want to grow 15 unit cell, so you will see the 15 unit cells. 15 oscillations basically. Okay, so this is the graph in where we see the intensity in the left y-axis, and in the x-axis we see the time, with the time how the oscillations are coming up. And in the inset, if you see the diffraction pattern, where you see the streaky pattern. Okay, so the left hand side is the streaky pattern which we observed on the pure STO, the substrate which we have TiO2 terminated substrate which I have used, and the right side is the film when we grow the film, and that kind of streaky pattern. So what this streaky pattern is representing, it is representing that they are in the 2-dimensional growth. And if it is a patchy kind of thing, then it shows the like dots kind of thing comes, then it shows that it is a 3-dimensional growth. So this results implicate that we have grown the 2-dimensional growth material. And then moving to the B, so it is the cross-sectional TEM of our film. So you see there is LSO on ZTO. So there is, we say that there is no intermixing at the interface. So with this, we are saying that our interface is very clean. And also the D, the sad pattern of TEM is exhibiting the epitaxial nature of our film which we have grown. And same results we have seen in the theta to theta Xrd of our Xrd of thin film, where we see the LSO epitaxially grown on 100 plane. And 100 plane is the similar plane what STO is being taken off. Okay, so it is taking the pseudo cubic structure on the STO sample. And towards my left, if I see, there is a kind of, you see there is a terraces kind of structure you see. Okay, so what these terraces are showing, this is the AFM image basically of the substrate. Towards the left, that is A, and B is the film, that is 8 unit cell of LSO and STO. So this is very much important for 2-dimensional structures. These terraces and before growth and after growth, they have to be retained. And the step height is almost about 0.39 nanometer. Okay. So with these kind of structural things, we have shown that we have grown very abrupt, clean interfaces with the very epitaxial nature. So coming to the transport measurement, where we have measured the resistance as a function of temperature. If I see the left hand side top figure, it is shown for 3 different thickness, that is 4 unit cell, 10 unit cell and 15 unit cell. So if you see the material LSO3, which is as such in pristine, it is insulating. When we grow in the form of thin film, it comes down to the, because it is going down with the temperature, the resistance going, so it is a metallic nature is being observed. So it simply signifies that two-dimensional electron gas has been formed at the interface. And also in the inset we have fitted this mobility of these graphs. We have measured mobility also. So they have shown the electron-electron interaction in the films, which again signifies the two-dimensional gas at the interface. And the bottom figure in the left side, it is showing the NS. Basically, it is the carrier concentration, which is almost of the order of 10 raised to 13 per centimeter square, which is almost similar to the LO-STO structures only. However, for the mobility, if you see when we reduce the temperature, then the mobility at the room temperature, it is the order of 4 to 7 centimeters square per volt second. However, at 50 Kelvin, it is going up by 2 orders, that is 10 raised to 2 centimeter square per volt second. So now the what is exactly happening in the systems? For that, we have done the XPS. So for the XPS, if you see, this is the this is the representation for TI2P and the down one is TI2P 3 by 2. So here, if you see, there at 464 and in between 460, sorry, it's a 456, I think, yeah. So it is around 2 peaks are observed. So what is exactly happening actually? So if you see, the red one is for the 4-unit cell and the black one is for the 3-unit cell. So if you see the bottom figure, the B, so 4-unit cell, if you see, when we are crossing the critical thickness, that exactly at 4-unit cell, you see there is a kind of neighboring peak which you see. So this peak which is being fitted, so this maximum figure, maximum peak intensity which we are observing, it is for TI4 plus, and for this the next fitted peak is TI3 plus. So here what we see for 3-unit cell, there is no TI3 plus, but for 4-unit cell you get the TI3 plus. The kind of polar catastrophe model which we are explaining in the earlier slide. So the same thing has been followed in our system, and that result to the two-dimensional electron gas at the system. So very recently we have done this measurement this earlier we have already the student has published, but this particular is not published. So this measurements we have done with in ISC with Professor Avik. So in these systems we are also able to observe the superconductivity around, you can say 160 millikelvin. So coming to the non-stoichiometric CATA-O on STO. So why I am explaining this particular system along with LSO system, because one is the very much stoichiometric and this system comes out to be non-stoichiometric. But the properties has been almost similar. So this particular figure where the left hand side represents the bulk target material which we have made, it was of CATA2O6. However, when we are going the film, it is no more CATA2O6. It comes out to be something different, which we will see in the next slide. So again, we are able to grow the very epitaxial film of CTO by PLD itself. And coming to the structural details of the sample, as I will not go through again, oscillation and all, this again represent the clear unit cell by unit cell growth while we are growing the thin films, and the diffraction pattern again represent the two-dimensional growth of the films which we are growing of CTO on STO. And right hand side is representing the X-ray, where the C outer plane C has been come out to 3.9 angstrom, which is almost similar to the STO. So what is happening? There might be doubt that there is no extra peak is visible for the film, but it is almost overlapping. So the similar thing when we are doing with the reciprocal space mapping. So here also you see the film has been very much coherently grown on the substrate. So that is why this kind of Xrd pattern we are observing. And secondly, the phi scan of these films where you see these 4 peaks which represent the cubic symmetry of our grown films. So similarly for these films also we have done the cross-sectional TEM, where for on the 10 unit cell thick film. So here also we conclude that we haven't seen any kind of intermixing in our system. The substrate is there, and on top of that film is there in the 5 nanometer scale, and at 2 nanometer scale you can say. So very clean films we are able to see, and epitaxial nature again is confirmed by this Xrd pattern from the TEM. And coming to the bottom figure, the right one, this is the results from our RBS measurements, Rutherford backscattering. So what is happening? When we saw in RBS, we have started with CATA to O6. However, we land up that the ratio is, so ratio has to be, if it has to be stoichiometric, it has to be CA 0.5 TA O3. Okay. However, when from RBS we found that it is very much non-stoichiometric, and the ratio is about for calcium and tantalum comes out to 0.9 is to 1.1 or 0.8. That kind of error bar is there in the system. So this work the student has already published in the JALCOM. So this non-stoichiometric has been observed with the RBS measurements. So now coming to this resistance measurement with the temperature. Here you see like earlier for LSO, the critical thickness was 4 unit cell. However, for this, our critical thickness is 9 unit cell. That is, if you see for left hand side figure where I'm showing the resistance, the inset, the bottom inset, it shows for 8 unit cell, it comes out to be insulating. And above that, it comes out to be very much conducting. So this inset in the left side of inset is showing the graph of resistance as a function of thickness. So you see that after the 8 unit cell, 9 unit cell, the resistance goes in giga order range. So it turns out to be insulating. And but interesting part, which okay, I will just discuss in that in the next slide. And similarly, we have also measured the carrier concentration and the mobility in the 10 unit cell and the 15 unit cell. So in these kind of structures where we say that there is no stoichiometric observation of the materials, and then we cannot only talk about polar catastrophe model. So here we propose that this kind of conductivity in these films, it can be maybe of the lattice strain, might be because of the lattice strain, or the kind of vacancies which might be occurring while growth, because it is, as I'm saying, that since the calcium and tantalum ratio has been changed, the oxygen value is not 6 or 3, so it is something else. So this conductivity can be because of the oxygen, excess oxygen, or kind of non-stoichiometry. Okay. So the topic which I have taken, that this is the comparison, this particular figure which I have shown. Towards my left, it is LSO. Again, the resistance RT plot, and for CTO towards my right side. If you see for LSO STO, there is a very much gap for the particular thickness. Okay, how the resistance is going down, that is, the nature is similar. However, there is a very much huge change between each thickness. It means that the resistance is changing with the thickness. However, for non-stoichiometric film, if we observe, there is no change, almost no change with the film thickness. Okay, and similar thing we can also see in the carrier concentration and mobility change as well. So what we conclude from this comparison, though the films are being made at similar conditions, so there is a non-stoichiometry in the CTO film, which offers additional parameter to fine-tune the interface properties for practical applications. Why? Because we have shown that with the thickness, there is not much change in the resistance, which is very much required for some kind of practical applications. And so we also show that conductivity is not abruptly changed with thickness of film after critical thickness, and mobility is also not a function of film thickness. And this nature, which has been not yet observed for any of the oxide which has been reported earlier by any other groups. So is my time over? Dr. Seki? Professor Seki?
Yes, almost, I think.
Okay.
Yeah.
Fine. So this is, I mean, whatever I want to conclude, that I haven't concluded. This particular slide which I am showing, just because the question itself arises when I am getting the stoichiometry, non-stoichiometry in CTO films. So whether I have tried for stoichiometry or not. So yes, we have tried to get the stoichiometry by changing the laser energy density, or you can say laser energy. If you see the right hand side figure, this is 10.5 millijoule, 14.5 millijoule, 32.5, different energy densities or energy of laser we have used. And we are getting very much epitaxial films, and proper oscillations also we are getting, which exhibit the layer by layer growth. And so all the films we are getting the epitaxial. However, again, when we are going to RBS, that is measurement, then again we are observing that they are non-stoichiometric. This is particular table where we see this, if you see the tabular form, the energy density is varying. With the energy density, the calcium, tantalum and oxygen has a variation in the stoichiometry. Okay. So to confirm this, because sometime we doubt RBS because of the resolution and all, so we have gone for XPS measurement. So XPS also has correspond the same result, that the grown films are not being, if we are changing the energy densities also, they are still in the non-stoichiometric form. Like the tantalum is 1.65, oxygen is 4.64. The oxygen is basically in excess. So we are still working on these kind of system. I mean, as I said, all the films are conducting. So two-dimensional electron gas is still present, but the mechanism behind these kind of films are still need to understand. We need to understand. So we are still working on this, and hopefully we will get into something. And we have not done yet the superconductivity measurements. So probably that will also put some light on these kind of material, what is exactly happening at the interface. So with this, I will finish my talk, and thank you everybody for listening to me.
Thank you very much. Thank you very much for nice talk.
Thank you.
So any question or comment?
Yeah, it is little different than the topic was little different than the earlier topics. So
we have also one question in chat box.
Okay.
Can there be a to dig at the interface of semiconducting transition metal dichlorogenide like molybdenum sulfide 2 and so tungsten selenide 2? So how efficient is that as compared to dig at the oxide interfaces?
How? Sorry, I didn't get you. How?
How efficient is that as compared to dig at the oxide interface? Maybe this question is compared with the
MOS2 at 2-dig structures, which is MOS2 and these kind of structures. They are also, I mean, but there is a vast difference between these two materials, because the mechanism of the two-dimensional gas or electron gas or the 2D structures, they are the basically topological insulators. So they are very much two different families which we are talking about. So yeah.
Okay, and so Sabankar, you are raising hand.
Yes, am I audible?
Please. Yes, Shubhankar.
Hi, Anjana, it's a very nice talk. I just have a basic inquiry. You know that for LAOSTO case, people always talk about non-stoichiometry also drives this interface conductivity. So if you have LAO perfectly stoichiometry, then it cannot be, the interface cannot be stoichiometry. If you remember this Manhart paper and Triskan's paper, and you have seen in case of your this scanded material, this is naturally of stoichiometry, right?
No, LASC is not stoichiometry. CATA is non-stoichiometric.
Okay, so in that case, can you change the stoichiometry by doing something so that see that if this is the really case for your system as well or not?
For LASCO, you are suggesting for scandium systems?
Scandium systems?
Yes, I mean, good suggestion. But frankly speaking, we have done with the, we have changed the energy densities. So surprisingly, in those systems, we are getting the stoichiometry only. And we were not able to vary, but yes, we, because as you know, PLD has a lot of parameters which we can really play. So yes, we can definitely do. And I think you have one paper with this lanthanum stoichiometry. Yeah, I know that paper. Yes, yeah, I remember that paper.
Yeah,
so,
very nice. Thank you, Anjana.
Thank you, Shivanka. Thank you.
Thank you for the question. So we have another question in chat box. What is the physical origin of high intensity in the initial growth in lead oscillation?
Initial growth, oscillate. Okay. Initial, yeah. So I think the basic phenomenon when you talk about the layer by layer growth. So what is happening? Let us say that top layer of my STO, or you can take TiO2 termination. When the first layer comes, so if you see this 3 type of growth modes are there. So first it is coming with the kind of island, okay, and slowly it forms the layer kind of structure. So in that way only it is forming the oscillation. That is why the intensity is increasing when it is coming the this island, and then started the layer, the intensity started decreasing. However, when the second layer start coming, it is decreasing. So in that way, it is making the one oscillation. Now the question comes that why the first one is very high and then the kind of exponential decrease is there in the oscillation. So yes, with the kind of, because now the substrate, it is not seeing the substrate. Okay, so the kind of, you say, the crystallinity which we are observing with the substrate is slowing down, lowering down with the increase in the layers. So that is why the oscillations are slowly decreasing. The kind of intensity of the oscillation is decreasing.
Okay, I guess your answer is clear. Okay, thank you very much. And so I will pass you the moment. Could you please stop your screen sharing?
Oh, yeah. Sorry. Yeah, stopped.
Yes, this moment is for you. Thank you very much for your very nice talk. Thank you. Okay, let's move to the next talk. And next talk will be given by Professor Kohei Fujiwara in Tohoku University. He will give his talk about the topological Hall effect in multi-layers of Kagome lattice ferromagnet, iron sweeting, and platinum. Okay, Kohei, please start.
Takeshi, can you hear me?
Yes, I can hear you.
And see my main slide?
Yes, perfect.
Okay, thank you very much. Thank you, Mr. Chairman Seki-san, for your kind introduction. I'm Kohei Fujiwara of IMR Tohoku University. I have originally worked on the synthesis of oxide materials as the previous speaker talked, but stimulated by the recent big trend of topological materials and their potential applications in spintronics, I have recently joined this spintronic field. Therefore, I'm so happy to join this exciting workshop and interact with many eminent researchers. In this presentation, I'd like to introduce a new type of materials for the artificial control of magnetic skyrmion, that is Kagome lattice ferromagnet. By measuring topological Hall effect, I showed the validity of our approach. Okay, first of all, I would like to thank my collaborators and researchers who supported me in this study. In particular, Professor Seki and Dr. Kato of University of Tokyo made a great contribution to the experimental and theoretical progress. Also, Professor Kanazawa of University of Tokyo, who is the super expert of skyrmion physics, gave me helpful advice on the analysis of topological Hall effect. Magnetic skyrmion is a vortex-like swirling spin texture as illustrated here. Different from conventional spin textures appearing in magnetic domains and at domain worlds, skyrmion is characterized by its character as a magnetic monopole. This can be understood if you map the spins on a single point, for example, coordinates, origin of XYZ coordinates. Therefore, it behaves like a particle-like object. For example, by injecting electrical current or applying magnetic electric field, skyrmions can be manipulated. One interesting application proposed is the racetrack memory by combining a read-out device such as magnetic channel junction. Therefore, magnetic skyrmion is anticipated to be a novel information carrier in spintronics. In bulk study, the use of non-centrosymmetric crystals that lack inversion symmetry is known as an effective approach to induce skyrmions and skyrmion crystal phase. One representative system is B20 type compounds. Here, from pioneering work on mangan silicide, I show its magnetic phase diagram. Its ground state magnetism is helical. But at certain temperature and magnetic field conditions, unknown phase, here termed as A phase, appears, in which the formation of skyrmions was identified by neutron scattering measurement. As listed in the table taken from the Kanazawa-san's review, many compounds, including those show skyrmions even at the temperature higher than room temperature, have been discovered in non-centrosymmetric crystals. By using the chemical substitution technique, the size of skyrmion, the size and density of skyrmions can be controlled, as here visualized by Lorentz force microscopy. In the stabilization of skyrmions in non-centrosymmetric crystals, the so-called Jaroszynski-Moria interaction plays a key role. Hamiltonian of Jaroszynski-Moria interaction is written like this formula. Here, D is called the DMI vector that is related to the strength of spin-orbit coupling of the centered atom and defines the interaction of spins of the two neighboring magnetic atoms. To understand the effect of Jaroszynski-Moria interaction, let's consider a one-dimensional spin interaction, where the DMI term contributes to the energy in addition to the conventional exchange term. While the exchange term J favors parallel or anti-parallel configurations depending on the sign of J, the DMI terms favors a perpendicular one. This competition gives rise to a twist of spins that is a finite twisted angle. This is a fundamental unit of skyrmions. This DMI can also be activated by fabricating an asymmetric interface composed of a ferromagnetic layer and a non-magnetic layer with large spin-orbit coupling. The upper right panel shows the result of theoretical calculation of Jaroszynski-Moria interaction at the platinum and cobalt interface. You can see that strong DMI energy occurs in the interface cobalt layer just adjacent to the platinum. Different from the bulk case, now the materials forming the interface and their thickness become critical parameters. By controlling them, the magnetic skyrmion can be controlled. The isolated skyrmion and also skyrmion lattice can be created by the critical control of those parameters. As we have seen, the skyrmions are induced on a very delicate balance. The control of these parameters are essential for the stabilization of skyrmions in an interface system. However, this direction seems to lack an important factor. If you remind the bulk approach that employs non-centrosymmetric crystals, there is a chance to introduce a specific geometry of lattice to stabilize the skyrmions. One example is a triangular lattice with geometrical frustration. When two anti-ferromagnetically coupled spins are placed on the two of the three corners, the remaining side suffers from the two competing interactions. This may be beneficial for inducing twisted spin structure. We paid our attention to a triangular-based Kagome-lattice iron tin compound Fe3SN in this study. Iron tin binary phase is known to have three Kagome-lattice compounds, that is Fe3SN, Fe3SN2, and Fe3SN. These compounds contain a common structural unit of Fe3SN Kagome layer. Depending on the stacking manner of Fe3SN and SN2 layers along the C-axis, different magnetic properties arise. Recently, the topological properties of these Kagome-lattice iron tin alloys have been attracting much attention. Ferromagnetic Fe3SN2 has been reported to host massive Dirac fermions in the band structure and show large anomalous Hall effect at room temperature. In anti-ferromagnetic FeSN, the characteristic flat band structure has been observed by spectroscopy. Fe3SN may also be a topological magnet, but here I take advantage of its triangular-based lattice geometry. Bulk Fe3SN was reported to have in-plane magnetic anisotropy, namely the spins favor to lie in the Kagome plane. However, little has been known about the physical properties. One reason for this is this comes from the difficulty in the fabrication of high purity crystals. The Fe3SN and Fe3SN2 are high temperature phases in their binary phase diagrams. So to stabilize these high temperature phases, quenching is necessary. Also, quenching is a general bulk growth technique, but it's difficult to apply to thin film growth. In fact, the direct film growth on sapphire substrate resulted in a phase separation to thermodynamically stable phases. The high temperature phase Fe3SN was not obtained. Very recently, successful stabilization of the high temperature Fe3SN phase was reported by two groups by using a platinum buffer layer. I was very surprised at the role of platinum in the phase stabilization and got interested in the presence of platinum with strong spin-orbit coupling, because the hetero interface with platinum is very suitable for activating the interfacial Jaroszynski-Morier interaction. Here, I summarize my strategy. Starting from the Fe3SN thick films with bulk-like in-plane anisotropy and coplanar spin state, we reduce the film thickness T. If interfacial DMI Jaroszynski-Morier interaction is activated at the interface, it may twist spins, inducing perpendicular-like magnetic anisotropy and non-coplanar spin state, like skyrmions, below critical thickness here, termed as TMA. We verify this strategy by measuring magnetization and Hall effect, as well as performing numerical simulation. We fabricated a stack of Fe3SN and 10 nanometer thick platinum layers on sapphire substrates using RF magnetron sputtering. As listed here, each layer was deposited at different substrate temperature, and the top surface was capped with an insulating SiOx layer to avoid degradation in air. Hereafter, I call this basic structure as bilayer. The upper right panel shows a typical Xrd pattern measured for the Fe3SN thickness with over 8 nanometer. While intense peak of platinum 111 and 222 diffraction peaks are observed, the presence of other crystalline component is not clear because there are strong intensities and Raoult oscillations. By performing cross-sectional TEM observation and electron diffraction analysis, we identified the formation of the Kagome lattice Fe3SN phase. The relatively flat film was also observed even for a 1.6 nanometer thick film, which corresponds to the 7 Kagome layers. Based on these results, we control the film thickness T based on the sputtering rate and fabricate ultra-thin bilayer samples. Shown here is the magnetization versus field curves measured at 300 Kelvin. For bilayers with the Fe3SN thickness smaller than 1 nanometer using a skewed magnetometer. To compare the result measured in plane and out of plane magnetic fields, the magnetization values were normalized by the saturation values. In the most thick 0.8 nanometer thick bilayer, the saturation occurs more easily in the in-plane magnetic field, consistent with the in-plane magnetic anisotropy of the bulk. With decreasing the thickness, the two curves change systematically. Following the procedure widely used for the analysis of perpendicular magnetic anisotropy, we calculated the effective anisotropy field in the unit of Tesla, as plotted in the lower panel. With decreasing the thickness, the negative value in the thick bilayers changes its sign at about 0.48 nanometer and becomes positive. This indicates the change in anisotropy as I expected. Considering the platinum with strong spin-orbit coupling, the effective strength of interfacial Jaroszewski-Morier interaction will be increased in the ultra-thin bilayers, thereby modifying the originally coplanar state to a non-coplanar state, as reported for other metallic bilayer systems. To theoretically support this speculation, we performed a Monte Carlo simulation for a single Kagome layer. We considered ferromagnetic Heisenberg interaction J, single ion anisotropy A, and also introduced the interfacial DMI and bulk DMI contributions as the in-plane and out-of-plane components of DMI vectors. The simulation results under out-of-magnetic field using a reasonable parameter set is shown on your right, where spin solid angle subtended by neighboring 3 spins per 1 unit cell is indicated by color. In the upper left region, with large negative A values, spins rise in the Kagome plane, which corresponds to the thick film limit with bulk-like in-plane magnetic anisotropy. In the lower left region, spins point to the applied field directions, which corresponds to the perpendicular magnetic anisotropy. Both states have no net spin solid angle because spins are fully parallel. However, by introducing a moderate contribution of the in-plane D component, finite spin solid angle is generated. Very interestingly, the simulation predicts the formation of scandium crystal phase at the appropriate parameter conditions. In such ultra-thin films, it is quite difficult to directly detect the formation of scandions. So we evaluate it by measuring topological Hall effect. Hall effect can be measured by detecting a transverse Hall voltage generated perpendicularly to the current injected current direction. In magnetic materials, in addition to the ordinary Hall term perpendicular to proportional to the applied field, anomalous Hall term proportional to magnetization contribute to the Hall resistance. If the magnet has spin textures with finite spin chirality defined by this equation, additional Hall contribution arises called the topological Hall effect. This is because the spin chirality produces a fictitious magnetic field for conduction electrons. As topological Hall effect is related to the density of scandions, we can evaluate the formation of scandions by measuring and analyzing Hall effect. Here I show an example of the topological Hall effect measurement and analysis reported for bulk manganese germanite sample. By fitting the measured Hall resistivity using separately measured magnetization data, we can extract the residual Hall resistance term. The solid curves in the left panels are the fits based on the ordinary and anomalous Hall terms. Clearly, an additional contribution is necessary to reproduce the experimental results. For example, please take a look at the results at 30 Kelvin and 20 Kelvin, in which the fitting curves largely deviate from the measured data. The residual Hall resistivity is here attributed to topological Hall effect, and its relevance to skyrmions is discussed. Let me move on to our results of Hall resistance measurements for the thin and thick bilayer samples. At 400 Kelvin, the thick bilayer with in-plane anisotropy shows typical anomalous Hall effect behavior together with the linear ordinary Hall contribution. In contrast, a clear hump-like Hall resistance anomaly occurs in the perpendicular-like anisotropy thin bilayer sample. The weakening of anomalous Hall effect is naturally understood by considering the vanishingly small magnetization at 400 Kelvin in the thin bilayer sample. Using this relation, we subtracted the ordinary Hall term proportional to the applied field and anomalous Hall term proportional to the magnetization, and found a significant residual Hall resistance in the thin bilayer sample, as plotted here. The physical origin of such residual Hall resistance has been intensively discussed. One possibility is, as mentioned before, topological Hall effect arising from non-trivial spin texture induced by interface Jaroszynski-Morier interaction. An extrinsic inhomogeneity-driven mechanism could also show similar behavior through the superposition of multiple anomalous Hall components with opposite signs. Here I show a typical example of the inhomogeneity case. If there are two anomalous Hall components with opposite sign, the superposition may produce such hump-like anomaly in Hall resistivity or Hall resistance. Strontium leucennate is very sensitive to the thickness. When the thickness is 4 unit cell, the anomalous Hall effect has a positive sign, but when reduced to increased to 5 unit cell, it changes the sign. Therefore, if there is a fractional thickness variation on the surface of a substrate, the opposite contributions may produce such hump-like anomaly. In fact, they systematically verified the existence of hump-like anomaly by controlling the fractional thickness. To exclude this possibility, we tried to reproduce the measured results by superposing some data taken for different thicknesses, but all the cases cannot reproduce the sharp hump-like anomaly observed. To further support the intrinsic topological Hall effect scenario driven by interfacial Jaroszynski-Morier interaction, we fabricated tri-layer structures where platinum, tungsten, and tantalum capping layer were inserted between the here not shown SiOx capping layer. If the interfacial Jaroszynski-Morier interaction is valid, in the symmetric platinum Fe3SN and platinum tri-layer, the opposite contribution from the top and bottom interfaces should fully cancel the low field resistance anomaly. while keeping the comparable anomalous Hall effect. Similarly, depending on the strength of the interfacial Jelsinski-Morier interaction, which should be proportional to the strength of spin-orbit coupling, a different magnitude of the Hall resistance anomaly should appear. Here we slightly adjusted the thickness of FE3SN layer so that the anomalous Hall effect becomes comparable. As expected, we observed the clear effect of the capping layer on the Hall resistance anomaly. In the case of the tungsten tantalum capping layer, top layers, partly remained weak topological Hall effect resistance anomaly were observed, whereas platinum layer completely suppressed the resistance anomaly as expected. These dependencies are fully consistent with the magnitude of the interfacial DMI. Therefore, the interfacial DMI intrinsic scenario is reasonable rather than the extrinsic inhomogeneity driven mechanism. Having verified the interfacial DMI origin, we obtained the topological Hall resistance from the Hall resistance data, as shown on your right. The results for 0.4 nanometer is shown here as a counterplot on the temperature and magnetic field plane. You can see the magnitude of the topological Hall resistance shown by color and its peak field, at which topological Hall resistance becomes maximal, increases with increasing temperature. To understand this behavior, we performed a finite temperature simulation and obtained results that is quantitatively consistent with the experimental results. This agreement strongly suggests that the spin texture like the scandium crystal, as shown by the magnetic phase simulation, exists in our thin bilayer samples. To extract the real space feature of the spin texture, we calculated the resistivity now of the Fe3SN layer on platinum using a parallel conduction circuit model, and estimated the topological Hall resistivity in the unit of ohm centimeter. Following the widely used equation for the discussion of scandiums, we calculated the average separation of scandium, which can be regarded as the effective size of magnetic scandium if it exists. Although the correct estimation needs further analysis, the obtained values of 10 to 31 nanometer are quite reasonable as compared to the reported values in literature. The direct observation of the spin texture using microscopy technique will be our future interesting topic. To summarize, in the ultra-thin Fe3SN platinum bilayers, we observed a change in the magnetic anisotropy and detected topological Hall effect consistent with the interfacial DMI origin. We hope carbonaceous ferromagnets will give new powerful options for the artificial control of scandiums towards its application in spintronics. Thank you for your kind attention.
Thank you. Thank you very much for a nice talk. Okay, so we have two questions. So questions from Kavita Sharma. Dr. Sharma, can you hear me?
Mute.
Okay, Spankao, so your turn.
Okay, thank you, Dr. Fujiwara. Very nice talk.
Thank you very much.
So you say that the iron 3 tin films which you have prepared, the TC is much higher than the room temperature? Because you see the topological Hall effect even up to 400 Kelvin. So what is actually the TC? The bulk TC you say about 700?
Bulk TC is above 700.
Yes.
But
for your films, did you measure?
Yeah, I measure the magnetization, but due to the decreased film thickness, the actual TC is about 400 Kelvin in the thin samples.
Okay.
But yet it keeps room temperature TC.
Okay. And thank you. And last question. You saw that the anisotropy changes from in plane to perpendicular around 0.48. Okay. So below 0.48, it is perpendicular magnetic anisotropy. And usually one expects to see the skyrmions close to that spin orientation transition. So I wonder in the last slide, you saw that the topological Hall effect was still there when you took the platinum and tantalum, but the thickness was 0.64.
Yes,
so
yes.
What is the explanation to that? Because at 0.64, it's already in plane anisotropy.
Yeah. Actually, I'd like to fix the thickness value for the fair comparison, but when I deposited tungsten and tantalum top layers on 0.4 nanometer thick Fe3SN, the anomalous Hall effect is strongly suppressed. It may be due to the dead layer formation during the sputtering of tantalum and tungsten. So for these two samples, I adjusted so that the magnitude of anomalous Hall effect becomes comparable to the 0.4 nanometer samples with platinum bilayer.
Okay, you are telling that although it is 0.64 nanometer, but because there is a dead layer, maybe the actual
probably. So
less.
What I want to say is, I think it's just a technical problem, technical issue.
Okay, I see that. Thank you. Very nice.
Yes, thank you very much for question. And so next is Professor Mudri.
Hello.
Yes, please.
Hello.
Yeah. This is bilayer thing, that platinum. Do you have a capping on top of iron 310?
Sorry, bilayer case?
Yeah, in the case of bilayer, when you are comparing this topological Hall effect with three things, platinum on both sides and then tungsten and tantalum. So I was wondering.
In bilayer configuration?
The slide that you were showing just a few minutes before.
This one? No? Sorry, I cannot catch up the point of your question.
Yeah. The first one.
Yeah, first one is a basic bilayer structure.
So is it just iron 310 or there is some capping layer on top of it?
The capping layer is SiOX, but it's inactive. Just a protection layer from the degradation in air. And it does not activate the interfacial DMI.
Yeah, okay. Thank you. That's right.
Thank you.
So Dr. Sharma, can you hear me?
I think maybe we can move.
Okay.
So you may kindly present the memento, and then I would like to request all to switch on the camera. We should take a group photo before.
Okay, first I'll give so Kohei to this memento, so digital memento. So thank you very much for your nice talk.
Thank you very much. Thank you.
And then so Spanka, so we request all the participants to switch on the camera to get the group photo right. So please switch on your cameras. We will take a group photo.
People are switching on. Yes, just few seconds. We need to wait. I think people are still turning on. It is also necessary for DST report, you know.
Yeah.
Yes.
So same as JSPS.
Yes.
So later, please pass me.
Yes. Okay, smile. Okay, I think we are done. Thank you.
Okay, thank you very much. Thank you very much for your
So
cooperation.
we can go to the next one. Thank you.
Yes. So let's move to the final talk in this session. So final talk will be given by Professor Muradharan from IIT Bombay, India. Can you hear me, Professor?
Hello, hi. Thank you.
Hi.
We can
okay,
start.
Now your screen is being sharing.
Sure. So
Good.
we can start right away.
Yes, I would like to introduce. So next
Sure,
talk will be given by Professor Muradharan. And so his talk is New Directions in 2D Quantum Materials and Interfaces with Large-Bar Interaction. Please go ahead.
Yeah, sure. Hi, everyone. Thank you, Professor, for the intro, Professor Seki. And my name is Bhaskaran. It's easier to call with the first name. And I thank you, Professor Shubhankar, for inviting me also for this nice workshop. And I'm actually a full-fledged theoretician giving this talk. So this is probably one of the very few theory talks here. So I've renamed my title as Spintronics using quantum materials and Rashba interaction in interfaces. So this is our group's handle and this is our Twitter. And I am from electrical engineering at IIT Bombay. So that kind of brings us to the point why I'm doing this much of physics. It all starts with the fact that, you know, life for the beyond Moore era, we started off studying transistors, but we've reached the stage of what next? And, you know, there are like a plethora of options. And I come from a device modeling, school. And so we started working on various spintronic devices, quantum materials, topological devices, ultimately with the ambition of developing platforms for spintronics, quantum technologies, and neuromorphic. So what we do is fundamentally only this, understanding current flow at the nanoscale that will ultimately give us the whole breadth to understand and exploit the future effects of the quantum nanoscale. So what we do is basically based on, you know, the Keldysh non-equilibrium Green's function technique, which literally translates to understanding a device from a holistic point of view. That includes the material aspects, you know, things like control, which I'll talk about, the interface aspects, and then finally the dissipative aspects. So this all started with the Keldysh non-equilibrium Green's function approach. I don't want to get into too much, but this is a two-time approach applied on a spinner, which eventually gives rise to various correlation functions. And using those correlation functions transformed into energy domain, we can get steady state transport defined by the retarded Green's function. Most specifically, we are used to, as theorists, transport that is based on the Landauer-Büttiker formalism, most of you would have heard, which is really about, you know, cars traveling in nice lanes from the source to the drain, and the chemical potential applied between the source and drain giving rise to the voltage and currents giving by some sort of a transmission function. Now, all this can be encapsulated in our formalism by taking into account, you know, the channel from an atomistic Hamiltonian point of view, which is simply like solving the Schrodinger equation. However, when you have the two contacts, you have a sort of a modified Schrodinger equation that really involves the inflow, outflow, as well as a source term. Now, based on that, we have this formalism, the ballistic transport, which today I'll be talking everything about it. Ultimately, by doing a lot of matrix operation, we get what is called the transmission function, which will be used heavily in today's talk. And basically the fact that currents through the device, whether your spin currents or charge currents, can be captured using this. We can also do dissipative transport when you have scattering and other effects, and that's a little more involved, but in our course of few years, we have developed a lot of transport models that include quantum transport with dissipative scattering effects, with spin bath, and as well as this very detailed simulation with stochastic magnet dynamics, as well as the Poisson equation. So these are the simulators we have developed in great detail. And this one I'm very proud of is the Spintronic Simulator on the left panel. I'll probably turn on the laser pointer. So this guy involves, actually analyzing realistic structures involving the spin torque devices, which involves the stochastic Landau-Lifshitz-Gilbert solver, micromagnetics coupled with the Geldish-Green's function technique, and of course, Poisson. Several works have come up. And these other works involve optoelectronics as well as materials modeling tool developed with the Korean Institute. So with this brief introduction of what we do, I'd like to move on to some of our new research highlights. A lot of my work was involved in Spintronics MRAM device modeling. And after that, we started getting into 2D materials and devices, as well as topological hybrid systems that includes the famous Majorana devices. Now, today, I won't be talking much about our development so far, which involves spin filtering devices and STT-RAM. I'll be more interested in talking about the quantum, basically topotronics, which is coming from a 2D perspective. And I'll talk a little bit about these topological hybrid systems. So just the last thing I would like to say, how we evolved our spintronics work. We started off with understanding multi-layer spintronics, which is basically the spin torque device, but with multi-layer spin filtering analysis. We first predicted, sensitive magnetic field sensors, followed by spin torque oscillator designs, followed by predictable memory cell models, and finally possible thermal switching, etc. All based on the development of the spintronic solver. However, that's not what I'll be talking about today. So we'll have to take one step ahead into topological devices, which I will really like to talk about, and the fact that we are using Rashba and quantum spin Hall effect in a 2D platform. There's a little bit of history on how we got into 2D. And this starts with our own collaboration with Professor Hirayama's group in Tohoku University. And from 2017, we wrote a few works in developing models for quantum Hall systems under nuclear spin interactions. They work on nuclear spintronics. And we have a few works with Hirayama Sensei's group, specifically about how the edge channels, as you can see here from our simulation, can actually interact with the nuclear spins, and specifically spin polarized edge channels, how they give rise to resistively detected NMR. We developed a very comprehensive simulation model that involves electronic transport at the Landau beauty curve, followed by the nuclear spin dynamics calculations. So these are a few works we developed. And from here, we moved on to more 2D works. So with this our brief introduction, I'd like to start into our real work of today. That's topotronics with 2D Xenes. So many of us know that 2D Xenes are these group 4 elements, which have a staggered hexagonal lattice, which is basically silicene, stannine, etc. Now, under spin orbit coupling, they can exhibit some interesting topological phases that include the quantum spin Hall and the quantum valley Hall. These are the typical band structures. The first thing I'm going to talk about today is design of a split gate structure, which is just going to come out in NPJ 2D materials and devices and applications, and it is already in archive. This is a tunable valley filter that is coming, a very realizable topological valleytronics filter device, which can give you very good valley polarization. The other one I'm going to talk about is using the Rashba and the antiferromagnetic interaction to give you a transistor device, which has a very steep subthreshold characteristic. This has just come out on archive, so I wouldn't really talk too much yet. So let's start with valleytronics. One of the most important things is to get electric field control of valleys. As you know, 2D devices have these two K and K prime valleys, and in a staggered structure also they appear. Some of the important ways people do valley control is valley Hall effect, and people do magnetic control. People also think about optical control. But the staggered 2D Xene structures, upon putting an electric field, opens up the possibility of the fact that we can also have an electric field control. And in fact, using electric field control, we can actually make a transition between the quantum spin Hall and the quantum valley Hall space. So with this, if you can form interfaces, you can have these 1D kink states that are forming between the quantum spin Hall and the quantum valley Hall, which can give rise to valley filtering options that we're going to talk about. So this is a paper that I will spend some time on, which is just going to appear this week, hopefully. I've been waiting every day to give a number, but it will get published this week, I think. Okay, so we're going to introduce this topological domain walls and how we can do valley filtering based on topological domain walls. Existing proposals based on an experiment is basically the fact that you can create this valley polarization using valley Hall states. This is actually a Nature Nanotechnology from 2016. But that has a problem because you have both the valleys, which are unidirectional, and more importantly, you cannot separate them out. And most importantly, those states can actually tunnel with each other, and this will not form a stable valley filter. So there was a small proposal back in 2016 about the fact that you can use spin valley filtering. So what we are showing is we can put this multiple gated structure, just like what the experiment was there. It's not like a theory proposal, but based on experimentally realizable structure and electric fields. What we could show is that we can actually, put positive and negative polarity in a, multi-split gate structure and get valley polarization, so +1 and -1. So let's get into that in a bit detail. So the challenges of, the valley filter that was initially proposed in the experiments is backscattering can really cause the valleys to interfere and not create a pristine polarization. Second is the currents also differ. When you want to receive or when you want to detect the polarization, one of the best ways to detect quantized conductance, because that will give you a discernible electrical signal, right? So the solution is that we have to spatially separate the valleys, and that's what we're trying to do. And so based on the typical Hamiltonian you have, which has the intrinsic spin orbit coupling, lambda as a parameter, and the electric field applied at the sublattices given by delta, we can actually create a gap parameter, which is a theoretical concept to see which regions have a gap and which regions are topological, and also what is called a valley spin churn number, which we have analyzed in the paper, but let's not get into too much of that. So the first thing we could show is that the gap parameter varies with the spin orbit coupling parameter. And specifically, you can get a very gapped region, and those regions can have specific valleys and specific spin polarization. Right. So what in the original experiments showed that you have two quantum valley Hall spaces, that is between the phase 1 and phase 2, and did not discern the spins. But here what we are showing is you can have what is called a spatial separation, which is called spin valley locking, and spin protection of the valley kink state. So basically we are forming the interface between the quantum spin Hall and the quantum valley Hall phase, so that you can get K and K prime in two different polarizers, just like a polarizer. So the device setup is kind of like this. So we have the top plate, which is actually a split gate structure, whose side view looks like this. You can put +V, -V, etc. in potentials. And based on this, what we found very interestingly is that you can have a gap plus region here and a gap region on the two sides of the. You can create a width of a gapless state so that you can have the quantum spin Hall propagating. And then you have a trivial state, which is kind of forming the domain wall between each other. So we can create a large junction width by putting the split gates a little apart, and then create hopefully a large spin orbit coupling to create a gapped region after that. So one of the things we, of course, have is the large spin orbit coupling and large buckling height. We have to look for materials, typically group 4 materials, germanine, styrene, plumbine, and arsenine, etc., and possibly 1T prime monolayer TM bases could work out. We still haven't done the materials calculation. So our idea is now to do with that Hamiltonian the transport calculation, and our metrics are typically the transmission and the valley polarization, right? So the transmission is given by the sum of the valley K and K prime. Just like you calculate TMR, you can calculate the valley polarization, right? TK minus TK prime divided by TK plus TK. We also add non-magnetic short-range disorder to our system. So this is our setup, and these are the states that we are going to work around. And this clearly shows that for a change of polarity in the gate, split gate bias, you can get a valley polarization of +1 and -1 in the ideal situation, showing these valley propagating states. However, we need to do more analysis. This is just a pristine and perfect case. So, when we need to optimize the structure, first we consider, various values of spin orbit intrinsic values. And we can see that, the polarization starts to degrade as you increase the spin orbit coupling, no problem. But as a function of the introduction of disorder, as you can see, when there is, no disorder, when you have a larger spin orbit coupling, first thing you notice is that the transmission becomes 1, showing that you have a nice, quantized transmission. But the valley polarization degrades and degrades further with disorder. Now, let's move. One more thing we need to do is, of course, to find what we have is a trade-off between the actual transmission, which is the electrical signal, and the valley polarization. And now we will see how it happens with the width. What really happens now is that the kink states, the domain wall that is formed from our simulation, as you increase the width and introduce the spin orbit coupling, you will see that you have these nice kink states on the edges forming the domain wall. And these are the states that give rise to the stable valley filter. Okay. So as I told you, now we analyzed with disorder, the transmission, as you increase the spin orbit coupling, does not degrade as much, but as you introduce a spin orbit coupling, the valley polarization decreases for large values of non-magnetic disorder. And furthermore, we could also compare what happens if you change the width of the channel, showing that at 20 nanometer widths, you can get appreciable valley polarizations at, not so much degradation in the total transmission, because you have to remember that when you detect anything electrically, the total transmission should also be discernible for electrical signals. So we then tried to optimize the width following our simulations. And based on that, we could plot as a function of the width. Width is this width between where the domain walls are formed. We could see that as you change the width, of course, the polarization falls down after some width and the transmission remains constant. So a lot of these details on the optimization of the device are presented along with the device model that we are showing here in this paper. So this is the first work I would like to show about the fact that, you can create interesting topotronic devices using this so-called concept of, interface engineering. The next part is this great infamous thing called the Boltzmann tyranny, which really tells you that, when you switch on a transistor, changing gear, the transistor that runs your computer, there is a slope of the transfer characteristics, that is the drain current with the gate voltage. And the steeper it gets, the better for your transistor operation. And today's transistors are saturated at 60 millivolt per decade due to the thermal switching, and this is called the Boltzmann's tyranny. Of course, subthermionic operation corresponds to reaching, steeper slopes. And there's a possibility of doing this using quantum field effect. So the very fact that you can induce a transition between a quantum spin Hall and an insulating state can also give rise to the transistor operation. But most importantly, the edge states can give rise to dissipation-less performance of the transistor. So this, coupled to topological edge states on the on and off, can give you something very interesting that can both beat the Boltzmann tyranny, also give rise to a counter-propagating edge states, the on state giving rise to dissipation-less operation of the transistor. So this is a recent submission. And so we're going to talk about this a bit. So this is a full-fledged model for any 2D Xene structure. Now, this is the various topological phases. What I considered in the first presentation is the quantum spill Hall, quantum valley Hall transition. But we can also have a vertical axis by introducing antiferromagnetic exchange, that is the transition between the quantum spin valley Hall and the quantum valley spin quantum anomalous Hall. So using these transitions, typical band structure, these are how the edge states propagate in these types of transitions, right? So using these and inclusion of Rajpa spin orbit coupling, which all can be electric field controlled in these devices, we'd like to show how to achieve topological field switching. So typically how this transistor works is you have this on state based on the quantum spin Hall, which is the horizontal transition, and an off state, which is the insulating quantum valley Hall state. Now we want to analyze a transistor structure that can give rise to the subthreshold performance, right? So we consider the structure, the buckle structure under the gate bias here. And of course, the gate bias relates to the, potential. So one of the most important things is that the subthreshold characteristics of the transistor is simply given by the on and off currents. So, and also in the on-off transition, we have the conduction band and the valence band current. And finally, the subthreshold swing is finally given by this 2.303 log, kT by Q, which is a 60 millivolt per decade, times an S star, which really tells you how the bands move with the application of gate voltage. As you can see, dE by dVg, dEc by dVg. So how the conduction and valence bands move tells you how the subthreshold slope varies. And now with the Rashba spin orbit coupling, you have a topological quantum field effect, which gives you this very interesting ratio of how the band gap moves with the application of the gate voltage. So let us get into the physics of this. The normal transistor on the left, right, is very simple. I'll just put everything here so that the animation doesn't mess up. Let's look at case one. So when you have a normal transistor, you apply a gate voltage, only both the bands move together. And so most of the current is conducted either by the conduction band current or the valence band current, that's NMOS or the PMOS transistor. And so the S star, which dictates a subthreshold swing, is approximately equal to 1, and 60 millivolt per decade is the limit. Now, in the topological field effect, on the other hand, the bands move in a very interesting way because this dEvg by dEg, etc., are very different, depends on the Rashba field effect. So the Rashba field effect creates a very interesting translation of bands when you put the electric field. Okay, so sometimes the limit can also be very bad as 120 millivolt per decade as the Rashba field effect is turned off. So as you turn on the Rashba field effect, you can actually get this to a much smaller value, which is what we'll discuss now. So based on our analysis, we could show that the quantum spin Hall to quantum valley Hall transition upon the introduction of the Rashba field effect reaches the limit of 120, which is not good for electrical engineers. So the next step is, of course, whatever we did was based on putting a symmetric gate bias, which is an engineering technique. So we can put an asymmetric gate bias by putting the second gate voltage to 0 and put all the gate there. Then what happens is you can get a steeper subthreshold swing as predicted by the Rashba field effect. But unfortunately, in the on state, you start conducting in the bulk. And that's not what you want in a topological state, because when you conduct bulk states, you're dissipating, and that whole effect of dissipationless currents is gone. So the last step is basically we introduce the antiferromagnetic exchange, which can be induced by the electric field, and then we can actually suppress one of the conduction band or the valence band currents as you change the electric field, and then you can see that we can actually reach a very steep subthreshold slope. And this is basically how we can overcome the Boltzmann's tyranny using these states that can come from various Rashba engineering. The first stage is this quantum spin Hall to quantum valley Hall, which was not good enough and gave us the not so steep subthreshold swing. But then by introducing the transition between quantum spin valley Hall and spin quantum anomalous Hall, we could actually get a very steep subthreshold swing. And this is a summary of our key points here, which is now presented in this archive paper. So lastly, I would like to comment that we're working a lot on the Majorana devices, which is also a Rashba interaction-based system. One of the important points is to to understand the Andreev reflection processes that give rise to what is called the Majorana zero modes, which are used in this topological quantum computing. One of the biggest controversies, as you all must have heard, is the fact that the nanowire system was not giving rise to the topological modes. And one of the things we are trying to understand is to now use this formalism and develop it on the Nambu spinor basis. And moving on, we have a lot of works on the nanowire device modeling, specifically considering the different types of scattering processes involved in the Rashba wire to the superconductor channel. One of the early works we showed is how phase breaking can influence the supercurrents in the Rashba nanowire. And then we have developed this into actual full-fledged models for the Rashba nanowire system. One of the latest works, which is of interest to this conference, is today people are looking at how the Rashba nanowire can couple to a superconductor and a magnetic insulator. These are called magnetic insulator hybrid nanowires. And we're developing a theoretical framework for this, which includes the scattering self-energy that comes from the bilayer magnetic insulator superconductor junction. And some of the new results we have is how the Majorana zero modes can actually happen at much smaller Zeeman fields compared to the original Rashba nanowire, and how robust the conductance quantization of the Majorana modes are. So with this, I'd like to kind of also state that I'm looking for collaborations in various aspects that start from 2D spintronics all the way to Majorana braiding and valleytronics. And last and second last thing I'd like to say is that I'm an editor in this journal from IOP, which is Materials for Quantum Technology. There's no APC until 2023, and it covers most of the topics that we'd like to, we've been discussing about. And I'm going to start hopefully a special edition in spintronics. And I hope you can submit to this journal when you have a chance. It's IOP journal. And this is the last slide. I thank everyone and the funding agencies and NICER for inviting me to give a talk here. Thank you very much. And you can follow us either on Twitter or on the website. Thank you very much.
Thank you. Thank you very much. Any other question? Any question? Yes, Nanda.
Hey, Bhaskar and Ranjit here.
Hello, yeah.
I just have a curiosity. Maybe I didn't follow it properly. So when you create this topological states, right? These are compound specific.
Yeah.
So did you examine all the compounds, those who have topological features, or how did you take that into account?
Oh, we started with only the Hamiltonian and varied the parameters as of now. We're looking for the actual materials as we move on.
Oh, okay. So this is just for theoretical formalism, not
this is a theoretical. We've developed the theoretical formalism ready to take the material aspects. So as we are able to get more serious material specific parameters, we can actually move on to the actual materials model. Right now, we have taken the generic Hamiltonian of 2D axenes.
Okay. So which is bound to create a edge state. That's what you are saying, right?
Yes, if you can realize quantum spin Hall, and those are the typical, this is the typical phase diagram of such a Hamiltonian. Now, it appears that some of these materials, spin orbit coupling, that's the only part we don't know how to engineer spin orbit coupling in these 2D materials. If there is a material with larger intrinsic SO and things like that, we can work. But one good thing is that, 1 minute, just last thing. One good thing is that this material was showing this quantum valley hole in this Nature Nanotechnology, which actually used the same ideas. And so I was just thinking that we could eventually get to this stage. Lastly, there is also Na3Bi material that my colleagues are actually working on, with whom we wrote this Boltzmann-Tirani work. And they are the Australian people from Monash, Michael Führer. So he is using Na3Bi material.
Yeah, so my only concern is that not only the spin orbit coupling, so you need to have some sort of symmetry conditions to induce a topological state.
Okay.
So
probably
a real material would help.
Yeah, we have to see that actually. Okay. That's very true. All these are still to be figured out at the materials level. I would really be interested in, that's why I kind of said in the collaboration part, I am looking for materials collaboration. Yeah.
Okay, thank you. Thank you. It was a nice talk.
Thank you.
Thank you. Thank you for the question. Okay, the time is over. So thank you very much.
Thank you.
Bhaskaran.
Thank you.
And so we should pass the moment for him. Yes, this is for you. Thank you very much.
Thank
for
you.
Your nice talk.
Thank you. Thank you very much. Appreciate it. Thank you.
Yeah.
Thank you very much.
Thank you.
So let's present also a memento for Professor Seki for chairing the session.
Thank you very
So
much.
Takeshi, it's a pleasure presenting again this plaque for you. We will send all the plaques to all of you by email. Thank you very much for sharing, and we are about time now. We should break till lunchtime. So we'll start at 1:30 p.m. Indian time, so about 36 minutes from now. I would request all the speakers who have talked and who are going to talk also, if you are available, kindly join the virtual platform frame. There are 2 discussion rooms I have asked where you can go and people can come and discuss with you. Okay, so I would request to join kindly during the poster session. But anyway, after lunch, we will have 2 talks and then we will have the poster session. Okay, so see you in 35 minutes. Thank you.
Thank you.
See you.
Thank you.
Bye. Bye.
Thank you.
Moriyama-san.
Hello.
Okay.
Yeah. Good
Okay,
afternoon, all.
start.
So we have a. So I got this message from the organizers that we'll start 5 minutes later because probably people are still eating. So please
Okay.
give us 5 minutes more.
Sure.
Okay.
Yeah. Okay, so I welcome you all in this second session. Sorry for a little delayed start because the last session went longer, and that's what organizers told me. So we are just waiting for a couple, 1-2 minutes more, and then we'll get started.
Hello.
Hi.
Yeah.
Can I share my slide?
Yes. Professor Moriyama, please go ahead. And I request Professor Indranil Sarkar to chair this session. Indranil is an associate professor at the Institute for Nanoscience and Technology. He is an expert on various topics in magnetism and spintronics. I request you, Indranil, to kindly chair this session, where we will have 2 invited talks and a poster session. Okay, it's all over to you. Thank you.
Thanks, Shubhankar, and congratulations to the organizing team for this fantastic conference, people together. So as Professor Vedanta already mentioned, so we have 2 presentations in this session, and thereafter we will have the poster session, the link of which is given in the program list. So our first presentation is by Professor Takahiro Moriyama from Kyoto University, Japan. And I request him to kindly start his presentation on spin dynamics and transport in antiferromagnetism. So Professor Moriyama, please go ahead with your presentation.
Okay. Do you see my slide? Okay. Good. Do you see my slide?
Yes. It's
okay.
It's coming. Yeah, it's coming. Yeah, it's there.
Is it
we
okay?
Can see.
Good. Okay.
Yeah, we can see.
Okay.
Yes, yes, we can see.
All right. Let me start. Good afternoon, everyone. First, I'd like to thank the organizers, especially Seki-san, Takanashi-sensei, and Dr. Vedanta and Dr. Sin for this opportunity to give a talk in this interesting workshop. I'm Takahiro Moriyama from Kyoto University, Japan. So yeah, okay. So this is actually me more than 20 years ago when I was a student having a fun trip to India, actually. So there, I was really looking forward to visiting again when I got this invitation to this interesting workshop, but it is unfortunate this time. I hope to have a chance to visit there again. So please invite me sometime in the future. Okay, so in this talk, I would like to show and discuss a recent result and related to recent results related to the antiferromagnetic spintronics. So I have 2 items to talk about today. The first one is antiferromagnetic dynamics and the resonance, where we demonstrate the control of the antiferromagnetic resonance frequency and the spin pumping effect coming from this antiferromagnetic resonance. And the second one is a spin current transmission through the antiferromagnet. Here we demonstrate the long distance transmission, maybe more than 100 nanometers, and also high speed transmission at the terahertz range. So I'd like to acknowledge in this slide. So this work especially I'm presenting here, was done in collaboration with various universities, domestic and worldwide. I also want to acknowledge various funding support to support our activities. So the antiferromagnetic spintronics is one of the exciting branches of the spintronics field. Comparing to the ferromagnetic materials conventionally used for the spintronics devices, antiferromagnet have much smaller susceptibility and no stray field, which might enable us to make a highly dense memory. And more interesting property of the antiferromagnet is its very high resonance frequency, which can go up to terahertz range. So therefore, these materials are one of the few potential materials working in terahertz frequency, and that could harness the terahertz technology and the spintronics. So the anti-ferromagnetic resonance is quite distinct from the ferromagnetic resonance. The left animation is a spin precession of the ferromagnet according to this equation of motion that you well know, you know well, where all the spins can precess in the same phase as the ground state. Okay. On the other hand, such a same phase dynamics is not allowed for the antiferromagnets. In this way, the increase of the exchange energy is basically inevitable. Because it can already maintain the anti-parallel configuration all the time. So this is why the exchange energy and or the exchange field comes into play in the antiferromagnetic resonance frequency equation, as shown as shown here. So if we plug in a typical values here, the resonance frequency easily can go up to 1 terahertz. Say here I plug in the 1000 Tesla for the exchange field, and then anisotropy field about 1 Tesla. Okay. So basically, in order to detect the antiferromagnetic dynamics for resonance, terahertz spectroscopy is basically necessary. So in our system, we use a continuous continuous wave CW frequency domain terahertz system shown here. So with this setup, we can do a transmission absorption measurement. Basically, we put the sample here in between the emitter and the detector. So this is a typical absorption spectrum for the antiferromagnetic nickel oxide. It's a typical antiferromagnet, where you can see a very sharp absorption right at the 1 terahertz. Okay. So with such a spectrum, we can characterize the damping constant from the line width as we do similar to the ferromagnetic case by using this equation. And also from the temperature dependence of the resonance frequency, we can get more important information such as intrinsic resonance frequency omega 0 at the 0K, as well as the new temperature of the material. So this is for the nickel oxide case, where we get the damping constant of 5 times 10 to the minus 4. And omega 0 is 1.1 terahertz, and the new temperature is a 523 K, which is basically consistent with literature variety. So from here, I would like to show how we can control the antiferromagnetic resonance. So based on this equation, if you want to control, say, the resonance frequency, you need to modify either the exchange field or the anisotropy field. This is very clear. So the easy way is to dope some cation into the nickel oxide, basically replacing the nickel ion to some other element ion to modify exchange as well as the magnetic anisotropy. So in this study, we particularly dope with manganese ion, which is a magnetic doping, and the lithium, which is a Hall doping, and the magnesium, which is a non-magnetic doping, basically enlarging the band gap of the nickel oxide, and see how the resonance frequency can be controlled. So here, the slide basically summarizes obtain the intrinsic resonance frequency omega 0, as well as the new temperature for various doping elements as a function of the composition concentration. So regardless of the doping element, both frequency and the new temperature decrease by the doping. But the degree of the decrease is quite different for each element. So by understanding, to understand that, we assume the new temperature should be proportional to the exchange field in the molecular field theory. So we have this quadratic relation between the omega naught and also the new temperature. So based on this relation, we just compare omega naught and the new temperature to have some idea what happens in these materials. So the manganese cation doping seem to decrease the anisotropy field, while the magnesium seem to decrease the exchange field. And the lithium doesn't have lithium doping does not have much influence to the resonant frequency as well as the new temperature. Okay, the next one is the line width or the Q factor change depending on the cation doping. So comparing to the Mg dope, the lithium dope, which are the non-magnetic doping, manganese doping seems to have a large effect on the line width enhancement as well as the Q factor decrease. So this magnetic doping effect might be related to the increase of magnetic inhomogeneity, which is a similar case for the ferromagnetic, where by introducing the magnetic inhomogeneity, we tend to have a larger line width. Okay, so we also investigate the doping effect on different material, such as, in this case, it's alpha hematite. So this material has a very long, very strong temperature dependence of the resonant frequency associated with the so-called Morin temperature, or Morin transition, at which the spin orientation changes by the strong temperature dependence of magnetic anisotropy energy. So here we find the aluminum, the ruthenium, and the rhodium, and the indium doping can dramatically modify the resonant frequency, as you can see. It's a time temperature dependence of the resonant frequency. So if you plot out all those resonant frequencies that those doping can control, we found that we can pretty much cover the resonant frequency from the millimeter wave to the terahertz wave frequency range. Okay. So another effect which influences the magnetic resonance generally is the so-called spin pumping effect. The spin pumping effect is an effect that the spin dynamics create and pump the spin current into the adjacent material. So this is basically widely examined in the ferromagnetic dynamics, but for the anti-ferromagnetic dynamics. Here we examine the spin pumping effect in the anti-ferromagnetic nickel oxide and the platinum structure. The sample used here is a nickel oxide platinum granule, where the platinum granules are dispersed in the nickel oxide matrix. So the detailed schematics of the spin pumping is shown here. The nickel oxide dynamics would pump the spin current into the platinum granule. The spin current will be dissipated in the platinum due to the spin orbit interaction, which results in the loss of a spin angular momentum. So we therefore should observe the enhancement of the magnetic damping described in this equation. So where G up down is so-called mixing conductance, the parameter which characterizes the spin pumping effect. And S is a nickel oxide platinum interface area, and B is a volume of the nickel oxide. So increasing G up down or S can increase the damping in this system. So this is just a structure analysis of the nickel oxide platinum granule samples. From the Xrd and also the optical microscope image of the cross section of the sample, we can see that the platinum granules here in this picture, the light bright area is a platinum, and the dark area is actually the ablation. It's a hole due to the ablation. The other area is the nickel oxide. So you can see the platinum granules and the nickel oxide matrix are well segregated. The temperature dependence of the resonance frequency is almost same regardless of the platinum composition. That means that the magnetic properties of the nickel oxide are invariant with the platinum granules. Okay, so this is basically the central result for it is aligned with as a function of platinum compositions. As you can see, as we increase the platinum composition up to like 10%, the line with or the damping increases. So basically, the more the platinum composition, the more the interfacial area is. So therefore, the damping increases in the framework of the spin pumping theory. So our estimation, our detailed estimation, I'm not talking the detail here, but our estimation of mixing conductance conclude that it is about like 12 per nanometer square, which is actually comparable to the ferromagnetic case where that's observed in permalloy platinum interface. And actually, this is the first time we get this mixing conductance at the interface of platinum and antiferromagnetic nickel oxide. Okay, so I'd like to move on to the second topic, which is the spin current transmission through the antiferromagnet. Okay, so the spin current, we all know that the spin current can be carried by the various medium. So for example, in the metallic materials, the electron can carry the spin angular momentum of the spin current. And also in the magnetic material, the spin current can be carried by the magnetic correlation or the spin wave or magnon. Okay. So in the context of the antiferromagnetic spintronics, the spin transmission in antiferromagnetic materials is one of the very interesting topics. So there have been various investigations of such a effect, including our own here, shown here. So we continue investigating the spin transmission in antiferromagnetic nickel oxide. So in particular, in this presentation, I'd like to show our recent work investigating how the spin transmission depends on the crystallinity of the nickel oxide. So again, here I'd like to explain briefly about the spin pumping effect, which can characterize basically the spin dissipation or spin transmission length in the material. So in the conventional spin pumping with a ferromagnet normal metal junction, the precessing spin pumps the spin current into the normal metal. Depending on the spin dissipation in the normal metal, the effective damping enhances. So by taking the thickness dependence of this normal metal, we can actually get the spin transmission length or the spin diffusion length of the material. This is a very famous paper written by Ms. Kami in Tohoku University. They characterize a spin diffusion length of the copper right here. Okay, similarly, basically, we made this kind of tri-layer composed of permalloy and an antiferromagnetic nickel oxide. And sometimes we put the platinum or do without platinum. So the experiment is done by basically using the homodyne FMR technique. And then we get this kind of FMR spectra, and from the spectral line width, we characterize the damping constant. So here is a spectrum line width as a function of resonance frequency for various nickel oxide thickness, from which we can obtain the damping constant. So by the way, this is about the polycrystalline nickel oxide case. So we get the damping constant as a function of nickel oxide thickness, something like this. By fitting into this data, we obtain the fitting using this equation. We obtain the spin transmission length of about 20 nanometer for polycrystalline nickel oxide. Well, this is this doesn't change even if we change the thickness of a permaloid. Okay, so the next thing we might ask will be how about the single crystalline nickel oxide? So we did such experiment. So we made a epitaxially grown nickel oxide. We made either 001 or 111 oriented epitaxial nickel oxide, and performed the same spin pumping experiment to characterize the spin transmission length. So this slide basically shows the central result. So as you can see, the damping behavior with respect to the nickel oxide thickness is quite different for 111 and 001 oriented nickel oxide. So the interesting thing is that there is no enhancement of the damping for nickel oxide 001 case. So this may suggest two possibilities. One is that the spin isn't really injected into the nickel oxide. So there's no spin current to the nickel oxide interaction. So there shouldn't be any damping enhancement. So this is a very trivial case for us. The other possibility is that the spin transmission is much longer than this thickness range, which will be something very interesting. So the additional experiments here basically confirm that the enhancement of the damping with the platinum at the end, suggesting that the spin current coming from the permaloid through the nickel oxide is actually reaching to the platinum. So from this result, we basically conclude that we have a 50 nanometer spin transmission length for the nickel oxide 111, and probably more than 1 micron transmission length for the nickel oxide 001. Okay, so now another question would be how fast can the transmission, spin transmission be in the anti-ferromagnetic material? So we tested this in the framework of the terahertz emission experiment in magnetic multilayer. The principle is basically shown in this picture. So the femtosecond laser pulse generates a transient spin current in the ferromagnetic layer, and it is injected into the anti-ferromagnetic layer. If the spin current reaches to the heavy metal layer, the spin to current, or the E field conversion, gives out the terahertz electromagnetic wave. Okay. So the experimental procedure, or the sample we use in this experiment is actually cobalt oxide is another antiferromagnetic material. The sample is basically tri-layer of the iron cobalt boron and the cobalt oxide and platinum with various cobalt oxide thickness. Okay, so the blocking temperature of this sample is between 200 and 300K, depending on the cobalt oxide thickness. So this is actually will be very important in the next slide. So just remember this blocking temperature is something around here in these samples. So again, our measurement is time domain terahertz spectroscopy using a femtosecond laser input and the terahertz wave output. And actually our setup is capable of measuring the polarization of the terahertz electromagnetic wave. So we observe the terahertz emission up to the cobalt oxide thickness of 5 nanometer, indicating that the femtosecond spin current is actually transmitting through the antiferromagnetic cobalt oxide. So if we look at the rotation of the terahertz polarization as a function of temperature right here, this sudden drop actually corresponding to the blocking temperature. Okay, so considering considering that the polarization of the terahertz E field is proportional to the cross product of the spin polarization sigma here and the flow direction J, this data basically strongly suggests that the terahertz polarization is affected by the near vector configuration or the twisting near vector in the cobalt oxide, just depicted in this cartoon. Okay, so basically our result here strongly indicate that there is a very fast interaction, like a sub-picosecond interaction of spin current and near order in the antiferromagnet. Okay, here comes the summary. So basically, I talk about the terahertz dynamics and the spin current transmission in antiferromagnet. Okay, thank you for your attention.
Thank you, Professor Moriyama, for this very beautiful so I don't see anything in the okay, maybe I will it was nice to see you called manganese. Why not?
Sorry, I cannot hear very well.
Okay, can you hear me better now? Hello.
Yeah.
Sorry. So the question is, we were trying to manipulate the magnetic anisotropy of oxide. You tried to substitute with magnesium or manganese or lithium. What was the motivation behind using these elements? Why not some high Z element or something which might have more high spin or effect?
Okay, so if I heard correctly, let me see. So yeah, you're talking about this one, right?
Right. Absolutely. Yeah. This one. Right.
Why did I choose these 3 elements? All right.
Right. Right. That is
okay. Yeah. So, well, not many elements can be substituted. The nickel cation in the nickel oxide, I think. And among those, I just picked up the magnetic doping. This, the manganese 2+ has a spin, right? So this is a magnetic doping. And why I chose a lithium is a whole doping. Basically, it has an effect that narrowing the band gap of the nickel oxide. So the electron correlation might be, increased, right? Yeah, can you hear me? No.
I think
anyway,
Professor Moriyama, I think Professor
okay,
Sarkar has
then the MG is a non-mag. MG is kind of, I think.
Indranil, I think you have some network issues.
Yeah, I think it's good. Now we have some more questions from chat. So maybe please go ahead and ask your question. So
yeah, I have a question actually. Professor Moriyama, can you hear me?
Yes.
Okay, so very nice talk. I really enjoyed. Towards end, when you showed these thin films of nickel oxide, and on top you have cobalt iron boron. If you could kindly go to that slide where you have taken a platinum underlayer. It was towards end of your talk.
This?
Yeah. So here, okay, cobalt oxide. So now you want to actually do the spin pumping using cobalt oxide. I mean, this is this magnonic based spin pumping, isn't it? Because it's an insulator.
It's not related to spin pumping effect. It is this one. We call this trihertz emission experiment. We just shine with very strong femtosecond laser, and it will actually excite the electron, which is polarized by the ferromagnet here.
Okay.
Okay.
I got
so
it.
This
so it is an
polarization.
Okay. All right. Sorry.
Yeah. So okay.
yeah. Any?
Yes. My question is, Professor Moriyama, if you go to the previous slide, you have a platinum underlayer. So what is the role of platinum there?
This one. Which I'm sorry. Which part are you talking about?
Here.
Oh, this one. Okay. Let me explain in this slide. Okay. So the FM is a permalloy in our case, and the AFM is a cobalt oxide or antiferromagnet. Okay. And the HM is a heavy metal. In this case, in our case, it's platinum. Okay. So as I just said, femtosecond laser pulse create a spin polarization in the ferromagnet, and it will be injected into the antiferromagnet. And if this is a spin current goes through the antiferromagnet and reaches to the platinum layer, it will create a current due to the inverse spin Hall effect. Okay. We inject the spin current into the platinum, we get the current, right? Or in this case, it will be the electric field because we don't have any short circuit. And this transient electric field will get the electromagnetic wave emission.
All right. So
this is very well established. I mean,
yes.
Without antiferromagnetic layer, it is very established experiment.
Yes. And now, what kind of thickness of cobalt oxide up to which you can still observe this phenomena?
It's about you can here. This is a result. It's well, if you characterize a spin, say transmission length, it's about I think 3 nanometer.
Okay.
By usual definition of the spin diffusion length. Yeah.
Okay. All right. Thank you so much. Thank you so much. Actually, the chairman, Dr. Indranil Sarkar, he has some issues with internet, so he just wrote me in WhatsApp. He has a power outage in his institute, so I will take over as the chairman from now. So are there any questions? Thank you very much for clarifying my questions, but if there are questions by others, kindly raise your hand or write in the chat box if you want me to read your question. Seems not the case, then I think it's a very clear talk, really nice. Thank you so much. I clap on behalf of everyone. And now I think volunteers, could you please kindly share the memento for Professor Moriyama? Yeah, Moriyama-san. So this is a pleasure to give this memento on behalf of all our organizing team. So I just read it for you. Indo-Japan Workshop on Interface Phenomena for Spintronics, jointly organized by Nitride India and IMR Sendai. Takes immense pleasure in presenting this plaque to Professor Takahiro Moriyama from Kyoto University in Japan in appreciation for being a valuable speaker to give a lecture on spin dynamics and transport in antiferromagnet. So thank you again so much.
Okay, thank you very much. I really like it.
Yes,
okay.
So we will send it by email, and I will also get in touch with you. Some interest are there on your work. I will write you. So please join the discussion after this talk, next talk, in the virtual platform.
Okay.
So we can also discuss there, and maybe others are interested to discuss too. Thank you very much.
Okay, thank you very much.
Okay, so the next speaker is Sujit Das. Sujit, I don't see you. Could you please put your video on?
Yeah, I'm here. Can you see?
Very nice to see you. So I'm
okay, nice to see you.
Please share your screen now.
Okay, can you see my screen?
Yes. Okay. So I'm very happy to welcome Dr. Sujit Das, who has recently joined as an assistant professor at the Material Research Center in Indian Institute of Science in Bangalore. Very young colleague, we welcome you to our Indian Spintronics community, and let's hope that we will do something together. And Sujit was working with Professor Ramauti Ramesh at UC Berkeley. I think most of the results you will probably saw from his postdoc time, but very interesting results. We are looking forward to your talk. So it's all yours. Thank you.
Okay, thank you. Okay, so first of all, thank you very much for this nice introductions, and thank you very much for invited me for this nice and interesting conference. So I'm going to talk about polar topology, a new era of ferroelectrics. The polar topology is a little bit different than the typical ferroelectrics. That's why it's a new era. So in the as Professor Vedanta told me already that I just recently joined Indian Institute of Science, and the work which I'm going to present most of done in UC Berkeley. So you can see the background image, these arrows, which is basically a dipole moment, and top you can see these hedgehog type of skyrmions. At the edges you will see that the negative capacitance regions with a block type of skyrmions. So this is a little bit complicated, so let's go on to details and know more about that. Okay, so in these talks these are the things I'm going to cover up. I will give a little bit background about the complex oxide and the topology, and then I will move to the model systems which we have grown by using laser MB, lead titanate and strontium titanate superlatics, and our observation ferroelectric or polar skyrmions. And if time will permit, I will show a little bit about the exotic phenomena like a negative capacitance regions of the polar skyrmions. And as we see the skyrmions, so it's defined by a well-defined skyrmion number. So if you give external perturbation, you can destroy these skyrmions and go to the uniform polarization. That means the topological phase transitions also we can see. And then I'll finish with a summary and outlook. So let's move on to it. So the perovskite unit cell or ABO3 look like that. Now, if you look at this unit cell, this green is the A atoms, at the center is the B atoms, and these B atoms is basically form an oxygen octahedra with oxygens, and red are the oxygens. Now, in a material, what happened? These octahedra rotations very variable because shape and orientation basically define the overall properties of the system through the crystal splitting or changing orbital overlap with the oxygen. Now, there are many exotic phenomena has been observed in oxides. A few examples like colossal magnetic resistance in manganites, first-rate magnetisms in pyrochlores, charge and spins types in cupettes, nickelates, and very famous high disease superconductivity in cupettes, nitrides, and also well-known 2D electron gas in lanthanum, aluminate, strontium titanate interfaces, and of course multiferroics like manganites and ferrites. Now, we can think about, instead of growing single crystal, we can start to create engineering heterostructures. Here is one example. So you can see this is a cross-sectional high-resolution transmission electron microscopy of the lead titanate and strontium titanate superlatics. The bright contrast is a lead titanate and dark contrast is a strontium titanate. Now you can see the interface. is a very sharp, coherent, no interdiffusion or dislocations. And we can grow this kind of materials by using the laser MB. And crystal chemistry of this perovskite is the same. Now, if you include a cation, you can play with the charge, orbital spin, lattice degree of freedom. And as I mentioned, the octahedral rotation tilts are very viable because these are the things which is basically define the overall properties of the system. Now, we grow all this material using the laser MB. So I don't want to go details about these techniques, but very briefly what happened, laser hit the target and create the plasma of the material and the opposite side substrate holding by a heater, and everything is happening inside the chamber. And then you need to apply the condition, oxygen pressure, temperature, grow your films, cool down, you will get a nanostructure film. And you can see how your layer growing by using the reflection high energy electron diffraction, RHEID. So here is a one of RHEID pattern. So this is a direct beam, and these are the diffraction pattern from the surface. Okay. Now, what we see during the deposition, we see the intensity, one of these diffraction pattern with the time. Now, if you look at the, let's say what happened for a layer by layer growth. For a layer by layer growth, what happened? Material start with the 2D islands, okay, and then it finish a complete layer. So once it finish a complete layer, if you look at the intensity, you will see a one oscillation. That's why you really have a perfect control in your material. For example, if you want to grow a 2 monolayer, so after seeing a 2 oscillation, you just stop the laser here. And if you want to grow 10 monolayer, after seeing the 10 oscillation, you just stop the laser there. So that's why you really have a control on your material. And today's talk is a topology, just a few slides. So what is a topology? Topology is a Greek word, and topology is meaning the studies the properties of a geometric object that are preserved under continuous deformation. Now, what are those continuous deformation you can think about? It can be an expansion, it can be a contraction, it can be a rotation. As long as you are not tearing them or you are not cutting them, they are preserved. Now, let me give an example and make it more clear. So if I give you some objects, let's say football, coffee mug, bowl, donut, pixel, and glass, and if I ask you, can you make a set of class? Then, so for that, you need to really have a characteristic definition, and then it's come like a called genus or topological invariant. It's basically counts the number of holes, and if you have this kind of characteristics, you can easily make a set of class. For example, like a football and bowl, it doesn't have any holes, so genus is 0, where your coffee mug and donut have only one hole, so genus is 1. In this case, 2 holes, genus is 2, and this one genus is 3. Now, for example, if you take a coffee mug and a donut, you can see the genus is both cases 1. So that means they are topologically invariant, equivalent. That means you can transform one to other by continuous deformation. You can see if you give a very smooth continuous deformations, you can, without breaking, you can transform donut from a coffee mug. So that's why they are topologically equivalent. Where if you look at the donut and a football, you cannot transform one to other by continuous deformations. So that's why they are not topologically equivalent. Now, in condensed matter physics, fermion is a well-defined topological object. But first, the Tony Fermi, who is a British physicist, first invented this fermion in particle physics. Now, in condensed matter physics, material science, these are really a hot topic. And generally, it's defined, it's act as a quasi-particle, and it's characterized by topological integer or topological charge, and topologically protected, means cannot be destroyed by continuous transformations. And here is an example how the magnetic fermions look like. This arrow is basically the magnetic spins at the local atoms, and this look like that. Now, also you can define the topological charge by this equation, where you use your normalized local dipole moment, and this integrand is called the fermion density, okay, or Pontryagin density. You can simplify this equation by taking the spherical polar coordinate. So your it will be like that. Your v is your vorticity, total rotation by 2 pi, and u is 0, your dipole moment at the center, and u is infinity dipole moment at the edge. And if you consider everything in your account and calculate the topological charge for the fermions, it will be always an integer number, either is a positive or negative. Now, once you have that, so there are different types of fermions have been predicted as well as observed experimentally, like Hedgehogs fermions, Bloch fermions, Hedgehog anti-fermions, Bloch anti-fermions, and this all based on their topological number. So for Hedgehog fermion and Bloch fermion, the topological number or fermion number is +1, where Hedgehog anti-fermion, Bloch anti-fermions, fermion number is -1. Now, first experimentally, fermion has been observed in magnetic material like a chiral magnet, like a manganese silicon, first observed by German group. They use Newton scattering and observe to the reciprocal space map. Okay, if you look at the QX and QY plane, you will see nice hexagonal lattice structure. And when they apply the magnetic field, this fermion is basically destroyed and make the uniform magnetization. Now, next year, 2010, by Tokura group, who is very well known in this magnetic fermion topic. So they observe real space observations of the fermions by using Lorentz transmission electron microscopy. And at low temperature and zero magnetic field, it shows like a helical structures. And when they apply the field around 50 millitesla, they have seen that nice hexagonal fermion lattice. And when they apply the high field, this fermion is basically again destroyed and make the uniform magnetizations. And the corresponding fast Fourier transform, you can see nice hexagonal lattice structure. Okay, so this was the start. Now question is, can we imagine the ferroelectric fermions? In the sense, can we replace the magnetic material by ferroelectric material and replace the arrow, which is a spin for a magnetic system, replace this arrow with a dipole moment? We can imagine the ferroelectric fermions. And this was the motivation. And now question is, what are the interaction parameters it could make this kind of structure? So if you look at the magnetic system, the competition of exchange interactions, magnetoelastic energy and anisotropy, and DMI interaction, which is antisymmetric exchange interactions, which is also part of total exchange interactions. And as you are applying the magnetic field, so Zeeman energy also playing a very important role. And so competition of all this energy in magnetic systems, fermion can be formed. Similarly, if you look at the ferroelectric systems, so basically the elastic energy, like which is coming from the strain, and electrostatic energy, which is coming from the boundary conditions, and these two energy playing such a way, there are another energies forming like a gradient energy, and that will form like a non-uniform polarization structure. Like here you can see like a vortex type of structure. So now we know this kind of competition of the energies can play an important role to have this kind of structures. And this is our model systems which we have grown like a lead titanate, strontium titanate superlatics, and on different substrate like a dysprosium scandate, SiGT, strontium titanate. The purpose of using these different substrate, because this will give a different elastic energy, means different strain, and that is very crucial to forming this kind of exotic topological structure. And I cannot go today everything, so I'll show a little bit these materials on dysprosium scandate substrates and details on strontium titanate substrates. And these are the deviation parameter I use. I just would like to skip that. Now, if you look at the parent compounds like a strontium titanate, the structure is a cubic and it's at room temperature, and it's a non-ferroelectric. If you look at the lead titanate, which is a tetragonal structure, and it's a ferroelectric. Now, if you look at the center atom, the ferroelectricity is coming. Look at the central atom, which is a titanium. Now, center atom is not at the center of the symmetry, rather is shifted. So this shifting is basically give rise to built-in spontaneous polarizations in the lead titanate. And interestingly, this material has a 180-degree domain walls, and that can be manipulated by strain or other boundary conditions. Now, so first, when we grow this material, lead titanate, strontium titanate superlatics on dysprosium scandates, so first observe the polar or ferroelectric vortex and how. So this is a dark field TM image, 10 monolayer lead titanate, 10 monolayer strontium titanate on dysprosium scandate substrate. So if you take a small part of this and take the high resolution image, and after that, what you need to do, you need to map with this ion displacement. So what I mentioned, that the ferroelectricity is coming because of this shift displacement from the center of this titanium 4+. Now, if you map this ion displacement on this TM image, what you're going to see, that you will see the polarization state, and which you will see in a zoom image, you will see the polarizations rotating like a clockwise and counterclockwise, like a make a vortex pair. And this is further confirmed by phase field simulation, which is done by our theory collaborator from Longcheng from Penn State University. So now, this is you are looking from the cross section. So what happened if you look from the top? So if you look from the top, you will see there is a long vortex tube extended over over 100 of micrometers. And you will see there is a dark contrast and bright contrast. That basically tells that the clockwise and counterclockwise vortex tube. And if you look at the X-ray diffractions, like a reciprocal space map, what we're going to see. So this is a you can do this kind of reciprocal space map either in a lab X-ray as well as a synchrotron. This measurement is done Argonne National Lab. It's at 003 reflection. So this is a substrate peak. These are the superlattice peak. Interestingly, if you look at the in-plane directions as well as the out-of-plane direction, you will see there is a long-range order, and that tells that this vortex has an in-plane and out-of-plane long-range order. Now, when we grow the same materials on strontium titanate substrate, so here's the material geometry. We use 16 monolayer lead titanate, 16 monolayer strontium titanate, and repeat it several times, make the superlattice. And if you look at the read intensity, you will see this nice oscillation of the lead titanate and strontium titanate, and that's very nice. The material grow layer by layer. Just want to inform you that we use the excess lead target during the growth. Why? Because our growth temperature is pretty high, so there is a chance to be a lead loss. So that's why it is important to use the excess lead in your target. But also we checked what happens if you don't use any excess lead target. So material doesn't grow layer by layer. And if you look at the read pattern, it's a 3D pattern. So that's why it's very important to have a excess lead in your target. Now, first, after grow the materials, we check the structure. So like a 2 theta omega scans, like a 002 reflection. This is a substrate peak. You'll see there is a nice superlattice peak, like SL plus 1, SL minus 1. And that tells that the superlattice is a well periodic and the interface is a smooth. And that is further confirmed by dark field TM image of the cross sections, lead titanate, strontium titanate, like a strontium titanate, lead titanate, strontium titanate. The interface is quite smooth. And we have done further structural characterization, like a reciprocal space map on different repeat superlatics, like a 3 repeat, 5 repeat, 8 repeat. And what we have seen, so this is a 002 reflection. So these are substrate peak. These are the superlattice peak. Interestingly, if you look at the in-plane direction, there is a side lobe, and that side lobe indicates that there is a skyrmion ordering. And if you take a section along the in-plane directions, what you will see that if you take a section along this line, which is QX and QY plane, you will see there is a 4 intense peak. And that 4 intense peak is basically telling that there is a potential 4-pole symmetry of these fermions. Now, this is according to the reciprocal space map. How about the real space? In real space, we need to do the transmission electron microscopy. So at the top view, the dark field TM image, you can see of the superlatics, you can see this small bubble structure all over the sample. While in a cross section, you will see there's a dark bright contrast, which is basically tells that the antiparallel domain configurations. Now, how do we prove these small bubbles are the skyrmions? So for that, we need again the polarization mapping. So for that, if you take a high resolution image of these bubbles from the top and map with the ion displacement, same like what I showed, so then you will see the polarization has like a hedgehog type of structures. And if you do the same thing for a cross sections, you will see the antiparallel domain configurations like this, and the interface is consistent with the hedgehog type of skyrmions. Now, this is at the top, and we use a 16 monolayer lead titanate. So what happened inside? So that we cannot do with a normal TM. So what we have done, we use the special technique like a 4D STM in collaboration with David Muller Group, Cornell University. Basically, he is a pioneer for this technique. So what happened in this technique, they use the scanning convergent electron beam diffraction. So that means it takes the diffraction pattern at every scan positions, and we know that the intensity difference of conjugate diffraction pattern will give you the polarity. And here, one of the alveolar dark field 4D STM image at the center layer, but still you are looking from the top. So very top is like a hedgehog type of structure, and this is a one of 4D STM image at the center layer when you are looking from the top, and this is corresponding polar mapping. So that means very top like a hedgehog type of skyrmions. At the center, polarization is rotating like that, like a block type of skyrmions. So that this is the beauty of this study, that it has a combination of hedgehog and the block type of skyrmions at room temperature, 0 electric field. And if you want to look at the 3D visualizations, which is done by our theory collaborator, so you can see top is like a hedgehog type of skyrmions, bottom also hedgehog type of skyrmions. This is the block walls, and these are the block type of skyrmions. And everything we have seen from the experiment as well. Now, once we see this kind of exotic structure, now question is, are these fermions is a chiral? If it is chiral, how do we prove it? So for that, first we need to know what is a chirality. Chirality is a geometrical property by which object is not superimposable on its mirror image. Means if you take a left hand and take the mirror of the left hand, that will be right hand. Now if you superimpose, they are not superimposed. Okay, that means handedness. Like a left-handed screw and right-handed screw, they are handed. Same way, like a fermion can be chiral as well. And how do we prove? How do we prove? By using optical activity like a Xrd second harmonic measurements, or also circular dichroism. This kind of measurements can prove the object is chiral or not. Okay, so now the question is, if I give you two fermions, okay, both cases the fermion number +1. One case is the helicity is left-handed, another case is the helicity is right-handed. As the fermion number both cases +1, that means they are topologically equivalent. So that means you can transform this to this by some external perturbations, either electric field or strain. Same way, if I give you two fermions, one is a fermion number -1 and one is the fermion number +1, and both has a right-handed helicity, as that they are not topologically equivalent because the fermion number is different. So if you want to transform this to this, you need to go through a topological phase transitions. Okay, why I'm showing this? This is just a take-home message that the chirality is not a topological number. It's just a property, just a take-home message. Now, how do we prove our object is a chiral or not? So we use the resonance of X-ray diffraction. So what is that? So we use like X-ray aberration spectroscopy plus X-ray diffraction. So first the X-ray aberration spectroscopy, little bit about the basic. So the X-ray aberration spectroscopy is basically probing the electronic transitions from field 2p to 3d orbitals. For example, our titanium 4+, and it's sensitive to local environment like oxidation state, cation side geometry. Now, if you take an energy scan of this titanium 4+, you will see these 4 peaks, and every peak has a meaning. So first 2 peak, like the transitions P3 by 2 to 3D transitions called L3, and last 2 peak transition P half to 3D called L2. And in the resonance of X-ray, we use the X-ray diffraction plus X-ray aberration spectroscopy. For example, if you take a reciprocal space map of your vortex samples, you will see these implant satellites. Now, if you do your X-ray aberration spectroscopy in this particular cube, then it's a resonance. Okay, and we use this technique to verify that our object's fermions is a chiral or not. So if you do that, so what we have seen that, so this is a reciprocal space map which I already showed several times. So 002 reflections. So these are the superlative peak, and this side lobe is due to the fermion modulations. Now, in this particular cube, if you take a resonance of X-ray, what you're going to see that you can see this diffraction pattern. Now, on this diffraction pattern, if you tune your energy at right circularly polarized light and left circularly polarized light, you will see the spectra look like that. After that, what you need to do? You need to subtract this background. If you do that, the spectra look like that. Once you take the difference, which is a X-ray circular dichroism, and we will see this finite peak at the L3 T2G edge, and that it tells that the T2G orbital has these helical rotations. Now, if you do the same thing for a negative Q, you will see this peak is flipped, and that's actually this peak is flipped, and that's actually a telltale signature that the object which we are seeing, which is a chiral. And the same type of experiment also you can do for polar vortex, where also we have seen this kind of finite peak at the L3 T2G edge. That's also tells that the polar vortex also chiral. Now, I would like to show a few more things that what happened if you apply the electric field on these fermions. So here is a phase field simulations. So they apply the electric field out of plane direction and look at the fermions. Now, when they apply the field under the field, the fermion is basically shrink when the field is very high, like a 1500 kilovolt per centimeter. The fermion is completely destroyed and make the uniform polarization. Now, how do we prove experimentally? That experiment will be tricky, so we need a lot of device fabrication first. So very quickly, the device look like that. In platinum side, we wire bond with a chip holder for applying the electric field, and this side we shine the X-ray. The real device look like that. Now, when by applying the electric field, we did the reciprocal space map at the synchrotron. So what we have seen? So zero electric field, this kind of reciprocal space map we already have seen. So these are substrate peak, these are the superlative peak, this side lobe is due to the fermion modulations. Now, under the field, what happened? So under the field, if you look at carefully, you will see the substrate peak intensity or superlattice peak intensity doesn't change, where the skyrmion peak intensity is reduced. Why? As under the field, the skyrmion is shrinking, the scattering probability of X-ray also less. As a result, this peak intensity reduce. Now I cannot show all the reciprocal space maps. So what I can do, if you take a line scan along this peak and plot with a different electric field, what we will see, this peak is coming due to the skyrmion. Now around 1500 kilovolt per centimeter, this skyrmion peak is completely destroyed and make the uniform polarization, which is deadly match with the simulation. Now if you take a appearance of the peak is a skyrmion number 1, when this peak is disappear, the skyrmion number goes to 0, and that's an indication of topological phase transitions. And the same type of experiment also we have done with the temperature around 600 Kelvin. This skyrmion peak is destroyed and make the uniform polarizations. Again, topological phase transition under the temperatures, and we plot this skyrmion number with the electric field and temperature, where the skyrmion number goes 1 to 0 around 1500 kilovolt per centimeter, and at temperature like a 600 Kelvin. With this, I would like to summarize my talk that we really can grow this kind of materials in a controlled way under strain or other boundary conditions. And also we can see many exotic properties like a slow dynamics of the skyrmions. If we apply the electric field of this skyrmion or vortex, if we apply the electric field of this vortex and stay there, the intensity is reduced very slowly, and when you take out the field, it immediately come back to its own states. So like a slow dynamics we can see, and also you can shine the light, and you will see this vortex can form like a supercrystal like behaviors. There are many interesting phenomena one can see from this kind of experiments. So with this, I would like to acknowledge my collaborators like Professor Ramesh and Len Martin, and also other collaborators, and of course the funding committee like Moore Foundations and Quantum Material from Berkeley Lab and Happy Electronics. So with this, I would like to stop here.
Yeah, thank you, Sujit. Really nice presentation and excellent results. This is this, the electric polar skyrmions. The complementary of magnetic skyrmion. It's a very, very interesting topic. So I think this brings a new era to this whole thing. So very nice to hear. Thank you so much. So on behalf of everyone, I clap for you. Now the talk is open for questions. So please raise hand or write in chat box. Okay, there are some questions in the chat box by Pradeep. He is one of our former students from NICER. Thanks for the interesting talk. I would like to understand if these ferroelectric skyrmions can be moved, and what about their dynamics?
Yes, that's we are working on it. That's very interesting questions. I mean, we are planning to make some interdigited in-plane electrode and trying to apply the electric field and see they can move or not. But unfortunately, they are so much coupled that they don't want to meet, rather than they distort it. Okay, so we really need to find some other type of measurements, maybe some optics or acoustic phonons, this kind of measurements that could maybe, I mean, at this moment, we are not sure how to move. But for sure, the electric field is not playing a role for movement, rather than is deforming only.
Yes.
And these are very nice questions. These are future work.
Yeah, I mean, just a follow-up question of Pradeep, like in the magnetic skyrmion, you have this topological Hall effect that they move. I think that is what he's asking particularly. Do you expect or anticipate that similar effect can come also for these polar skyrmions?
We first of all, these things we already thought about that. So what will be the counter experiment for a polar skyrmions, like in a topological Hall effect for a magnetic skyrmions?
Yeah.
So that kind of experiment is still not defined, but some kind of, we are thinking like a phononic Hall effect. That could be possible to see this kind of features.
Yeah, but first of all, I mean, is it possible to move the polar skyrmion?
Even see, look, without moving also you can see the magnetics, the topological Hall effect, because of the spin structure is different. a non-linear spin structure. So here we have a non-linear polarization structure. So in principle, we could see that signature.
Yeah, and I'm just curious towards the end. Actually, I have also some internet issues. So is it possible to move? Forget about distortion or trajectories, but is it possible to move them from one place to other by some kind of?
That's we are trying, but so far we are not succeed.
Okay, then it has to be explored in future.
Yeah, we need to explore, and we are going to do that.
Yes, definitely. All the best. There is a question by Anjana. Why are you calling the system laser MB?
Well, so this is basically read assistant pulse laser deposition technique, but newly called, if there is a read system attached with a PLD, people are start calling laser MB rather than the conventional MB. But it's a PLD basically.
Yeah, so it's a PLD. That's what she also write, that it looks.
Yeah, it's a PLD, but in the recent time, the terminology is changing slowly.
Okay. All right. Very good. So are there any other questions? Maybe I can ask one more question.
Yeah.
Again, something from intuition. I'm wondering, Professor Ramesh has done a lot of fantastic work on this magnetoelectric multiferroics. Now, do you think will it be possible to have a coexistence of these polar and magnetic fermions in same lattice?
Actually, I submitted few proposals on this topic.
Okay.
So I'm going to work on that.
Oh, great. Okay, then that's already
for sure. If you're interested, I can discuss more elaborately.
Yeah, we can discuss. But okay, but this is already in the pipeline. That's good to hear.
Yes.
So intuitively, it is probably possible, and
yes, it's possible. It's possible. Yes.
It's a strong material science, but also a lot of.
So basically, you are talking about some multiferroic materials to see this kind of, and yes, it is possible, and yeah, you will see the results maybe within 2 years.
Oh, great! I'm looking forward to that. Okay, so if there are no further questions, I think Sujit, you can stop sharing, and I'd like to request my team to share the memento for Professor Sujit Das. Abhishek? Yeah. Well, Sujit, I read it for you. On behalf of the organizing team of Indo-Japan Workshop on Interface Phenomena for Spintronics, which is jointly organized by NICER and IMR, we take immense pleasure in presenting this plaque to Professor Sujit Das from Indian Institute of Science, Bangalore, in appreciation for being a valuable speaker to give a lecture on polar topology and new era of ferroelectrics. So thank you so much. And Sujit, again, I'm very happy that you have come back to India, and I'm along with many others looking forward to your nice research work, and I'm sure you will be very full and will really significantly contribute to this very exciting topic. So thank you again.
Thank you.
Can you, Abhishek, please share? Yeah, great. Unfortunately, Professor Indranil Sarkar's internet has gone bad. I just had a word with him over phone. Nevertheless, I like to present this plaque to him. So we take immense pleasure in presenting this plaque to Professor Indranil Sarkar from INST. So now I think we can go to the frame platform. So I like to thank both the speakers, Professor Moriyama and Professor Sujit Das, for giving excellent talks. And also in the morning, we had really nice talks. Well, sorry, I was one of the speakers, but I'm talking about other talks. They were all very nice. And I request all the speakers who have finished talk and who are also going to give talks tomorrow, if you are around, kindly join the frame platform. The links has been sent to you by email. If any of you do not find that email link, please write in the chat box of the Zoom. It will be still active in parallel. Then we can help you out. And I request all the speakers to join the discussion room. Or you can also go around with the poster room, but please spend some time in the discussion room so that if there are questions or discussions or for collaboration or whatsoever, people can interact with you. So thank you. See you in the frame platform. Thank you.